There is a star hurtling through space right now. You can't see it. It doesn't shine brightly enough. It doesn't flare like a supernova or pulse like a dying white dwarf. But it is coming. Slowly, inevitably, it is gliding toward us through the black vacuum of interstellar space. Its name is Gliese 710, and though it travels in silence, its arrival could change everything. But before we continue, subscribe to the channel so you don't miss out on any of these videos. It's not a doomsday object in the traditional sense. It's not going to crash into the Earth, explode near the Sun, or swallow planets whole. But the threat it carries is subtler, and in some ways far more terrifying, because Gliese 710 isn't bringing the danger itself. It might unleash it. Gliese 710 is a real star. Not some theoretical phantom or science fiction creation. It has mass. It has motion. And most chilling of all, it has a destination, the outer edge of our solar system. Astronomers have known about passing stars for decades. The Sun moves through the Milky Way, and other stars move too. Sometimes those paths get close. But few get this close. Based on the best data we have today, Gliese 710 is expected to pass within just 10,000 to 20,000 astronomical units of the Sun, deep inside the Oort Cloud, that distant halo of icy bodies surrounding the solar system like a fragile, ancient shell. That may sound far, but in astronomical terms, it's incredibly close, about 1/4 of the distance to our nearest stellar neighbor, Proxima Centauri. And unlike other stars that whiz by quickly, Gliese 710 is moving relatively slowly, meaning its gravitational influence will linger, gently tugging at trillions of objects in that dark frontier. This isn't a warning for tomorrow. The event won't happen for another 1.3 million years. But in the scale of the cosmos, that's no time at all. It's already on its way. Every moment, every rotation of Earth, Gliese 710 drifts a little closer. Its approach is written into the future of our solar system like a chapter already set in ink, waiting to be read. The consequences could be enormous. Comets disturbed from their slumber in the Oort Cloud may cascade toward the inner solar system, bringing with them the risk of impact. Some could pass harmlessly by. Others might not. The history of Earth is already marked by such cosmic collisions, some mild, others catastrophic. Gliese 710 may be the next trigger. But this isn't just a story of risk. It's also one of revelation. The approach of Gliese 710 offers a rare window into the mechanics of our galaxy, the fragility of planetary systems, and the unseen forces that shape cosmic destiny. It's a reminder that while we measure time in years and lifetimes, the universe moves to a rhythm far grander. So as we look to the future, let us also look outward, to the space between the stars. Gliese 710 is coming. Not with fire. Not with fury. But with the potential to awaken ancient ice, to turn the distant edge of our solar system into a storm of stone and ice and gravity. It is a messenger from the void, and its message is one we are only beginning to understand. It's easy to imagine that a threat to the solar system would come from something colossal, like a supernova, a rogue black hole, or a wandering neutron star. But the object currently destined to shake the outer edges of our solar system isn't anything so exotic. It's a small, quiet star, an orange dwarf, nestled now within the folds of the Serpens constellation, far too dim to catch the eye without instruments, and yet destined to come closer to us than any star has in recorded memory. This star, Gliese 710, is what astronomers classify as a K-type main sequence star. It burns cooler than our Sun, with a surface temperature around 4,000 to 4,200 Kelvin, giving it that soft amber glow typical of orange dwarfs. It's smaller, too, about 60% the mass of the Sun and roughly 67% of its radius. With lower luminosity, Gliese 710 doesn't stand out in the night sky. In fact, its apparent magnitude is around plus 9.6, meaning that even with a clear sky and no light pollution, it remains invisible to the naked eye. You'd need a decent pair of binoculars or a small telescope just to glimpse it as a faint point among the stars of Serpens. But what it lacks in brightness, it makes up for in trajectory. Its motion through the galaxy is of far more interest than its physical appearance. Positioned currently at about 62 light-years, or nearly 19 parsecs, from Earth, Gliese 710 is drifting inward toward us, pulled by the same gravitational dance that moves all stars through the spiraling arms of the Milky Way. It doesn't travel with wild speed or reckless energy. Instead, it's deliberate, almost graceful in its path, a star among billions, obeying the unbending rules of Newtonian motion and galactic dynamics. What's striking is just how typical Gliese 710 is. It's not part of a binary system, has no known planetary companions, and emits no extraordinary radiation. Its spectrum is steady and unremarkable. But it is this very ordinariness that makes its future encounter so unsettling. It reminds us that even the most unassuming stars, under the right circumstances, can become agents of chaos, not by choice, but by orbit. Astronomers have catalogued Gliese 710 under various identifiers, most notably in the Gliese Catalogue of Nearby Stars and the Hipparcos Catalogue as HIP 89825. These naming conventions reflect decades of observational astronomy, with each catalogue offering refined measurements of stellar motion, position, and characteristics. Gliese 710 was once just another quiet entry in these long databases. Now it's a star of high interest, its future motion the subject of papers, models, and long-term simulations. And yet, even knowing all of this, it's difficult to truly grasp what Gliese 710 represents. It's a paradox, a star too dim to be seen, yet bright with implications, too small to rival the Sun, yet large enough to rearrange the outer solar system. It humbles us. It reveals that celestial influence is not only about brightness or power, but about timing, mass, and distance. There's something eerily poetic about it, a faint orange sun, quietly drifting through serpents, preparing to graze the icy edge of our system long after humanity, as we know it, may be gone. A reminder that in space, danger doesn't need to roar. Sometimes, it approaches slowly, lit in orange. Though Gliese 710 appears unremarkable in the grand theater of stars, its journey through space is anything but. To truly grasp the weight of its future visit, we need to trace its motion across the Milky Way, a motion governed not by chance, but by the relentless pull of gravity and the immense structure of our galaxy's spiral arms. Every star in the Milky Way is part of a massive celestial migration, including our own Sun, and Gliese 710 is no exception. It's been traveling silently through the galactic disk for billions of years, weaving a path shaped by the gravitational influence of stars, gas clouds, dark matter, and the collective pull of the galactic center itself. At present, Gliese 710 lies about 62 light-years from Earth. That's approximately 584 trillion kilometers away, an immense distance by any human standard, yet astonishingly close when one considers that the Milky Way spans over 100,000 light-years. From its location in the Serpens constellation, Gliese 710 moves with a speed of roughly 50,000 kilometers per hour relative to the Sun. It's fast in terrestrial terms, yes, but among stars, it's considered to be moving with a modest pace, especially when compared to high-velocity stars or runaway neutron stars tearing through space at hundreds of thousands of kilometers per hour. But speed alone doesn't determine danger. What matters is trajectory. And Gliese 710's trajectory is precisely what makes it extraordinary. Unlike most stars, which pass through the galaxy at a safe distance from the Sun, Gliese 710 is on a direct path inward. It's approaching the solar system along a nearly head-on course, with low relative tangential velocity, meaning it's not just grazing past us like so many other stars. It's on a collision course with the Sun's gravitational sphere of influence. This trajectory isn't a guess. It's been calculated with incredible precision using data from missions like ESA's Gaia Observatory, which has revolutionized astrometry, the science of measuring the positions and motions of stars. Gaia's observations provide not just the position of Gliese 710 at a single point in time, but a full map of its motion through three-dimensional space, how it moves sideways, its proper motion, how fast it's moving toward or away from us, its radial velocity, and how those combine to plot its path through the galactic fabric. What we find is chilling. As Gliese 710 moves through space, its orbit around the center of the galaxy happens to intersect with the Sun's. Not in the sense of a direct collision, but in the sense that it will pass through the solar system's outskirts. And given the vast amount of time between now and its closest approach, estimated at roughly 1.29 million years, we can predict its path with an astonishing degree of confidence. The Sun and Gliese 710 are like two cars on separate highways, slowly curving toward the same intersection, fated to pass at close range. Its journey hasn't been sudden. For tens of millions of years, Gliese 710 has been drifting toward us, unnoticed and unremarkable. It didn't come from some distant galactic arm or a chaotic cluster, it's a product of the same galactic neighborhood. It has always been here, a local traveler like the Sun. But because of the precise way stars orbit the Milky Way, elliptically, in and out of the galactic plane, occasional near misses are inevitable. Gliese 710 just happens to be the one whose approach is not amiss. The trajectory of Gliese 710 is still being refined, but based on its proper motion, radial velocity, and parallax, all measured to high accuracy, it is on course to penetrate deeply into the solar system's distant frontier. It's not a rogue star ejected by some cataclysm, it's part of the natural flow of galactic motion. That may be what makes it most dangerous, because it reminds us that we live not in a stable, isolated bubble, but in a swirling, shifting galaxy where stars routinely pass close enough to stir the architecture of entire solar systems. As of now, Gliese 710 continues this silent plunge inward, with every tick of the galactic clock bringing it infinitesimally closer to us. Each year, it crosses just a tiny sliver of space. But over the span of 1,000,000 years, that sliver becomes a straight line, cutting across the stars, aimed directly at the solar system's icy edge. The silence of space can be deceptive. While the night sky appears calm and timeless, vast motions are unfolding, stars drifting across the galaxy, invisible currents reshaping the architecture of stellar neighborhoods. One such motion belongs to Gliese 710, a faint orange dwarf whose quiet approach marks one of the most anticipated stellar encounters in the foreseeable future of our solar system. It's not just passing by. It's heading directly toward us, and the precision of modern astronomy has allowed us to peer forward in time to a moment when Gliese 710 will reach its closest point, a predicted cosmic rendezvous about 1.29 million years from now. This isn't just speculation. It's the result of cutting-edge data analysis drawn from the Gaia Space Observatory, an ambitious mission launched by the European Space Agency to map over 1 billion stars in our galaxy with unmatched accuracy. Gaia's measurements have been nothing short of revolutionary. Its ability to track the position, movement, and velocity of stars in 3 dimensions has transformed what was once a field of educated guesses into one of stunning precision. Using Gaia's data, astronomers have been able to chart Gliese 710's path forward through time. And what they've found is astonishing. In approximately 1.29 million years, Gliese 710 will make a near-parabolic flyby of our solar system. Its course will not intersect with the orbits of any of the major planets directly, but that's not the concern. The true danger lies farther out, in the solar system's distant frontier, a region almost untouched by human exploration but vital to our cosmic stability, the Oort Cloud. The predicted timing, 1.29 million years, isn't a vague round number. It comes from high-precision modeling that incorporates Gliese 710's current velocity vector, proper motion, and distance. The models take into account the gravitational influence of the Sun, perturbations from other stars, and the overall dynamics of the Milky Way. By integrating these variables into complex simulations, astronomers have essentially rewound and fast-forwarded the motion of Gliese 710 and the Sun in the galactic reference frame. Their conclusion: the two objects are on paths that will bring them within striking distance, cosmically speaking. What makes this even more unnerving is the star's low relative velocity. Gliese 710 is moving toward us at a speed that is unusually slow for a passing star. Many stellar flybys involve stars that zoom past the solar system at tens or hundreds of kilometers per second, minimizing the time they can gravitationally influence anything in our vicinity. But Gliese 710's approach is gentle, almost leisurely. It will pass close, and it will do so slowly, giving its gravitational pull time to take effect, especially in the fragile outer boundaries of our solar system. The forecast for its closest approach varies slightly depending on the model and data set used, but most estimates fall within the range of 1.25 to 1.31 million years from now. This variation stems from slight uncertainties in the star's exact mass, position, and motion, but the central figure, 1.29 million years, remains the most robust and widely accepted prediction. Importantly, every version of the model leads to the same conclusion: Gliese 710 will pass closer to the Sun than any other known star in the foreseeable future. This prediction marks a shift in how we understand stellar motion and its consequences. In the past, we could only react to cosmic events long after they had occurred: supernovae, gamma-ray bursts, or rogue asteroids. Now, for the first time, we are peering forward with confidence into the long-term future of our solar system's environment. And what we see is sobering. Even though the event lies over 1 million years in the future, the mere fact that it can be predicted at all is a testament to how far astronomical science has come. It speaks to the precision of our instruments and the clarity of our understanding of galactic dynamics. But it also raises profound questions about our place in the universe, and how prepared, or unprepared, we are to deal with the long-term consequences of such stellar encounters. Because when Gliese 710 does make its closest approach, it will likely come within a distance that places it deep inside the Oort Cloud, the icy reservoir of cometary nuclei that envelopes the solar system like a vast, diffuse shell. And that's where the real consequences begin, not from the star itself, but from the chaos its gravity might unleash. But before exploring those consequences, it's worth pausing to reflect on just how unusual such a close encounter really is. In the vast emptiness of interstellar space, the odds of any two stars passing within even a few light years of each other are slim. Yet Gliese 710 will come much closer than that. Some estimates place its minimum approach distance as low as 10,000 astronomical units (AU). That's just 0.16 light years. For context, Proxima Centauri, the nearest star to the Sun, is about 268,000 Australian dollars away. Gliese 710 is set to pass at a distance that's more than 25 times closer than our current nearest stellar neighbor. And unlike many other stellar visitors, Gliese 710 is not a transient or high-speed interloper. It's part of our galactic region. It's been part of our neighborhood for millions of years, slowly spiraling inward like a cosmic stranger coming home. Its impending arrival is not an alien invasion. It's more like a long-lost traveler finally crossing paths with us after eons apart. The scientific community continues to refine the details of this prediction. Each new data release from Gaia brings improved accuracy in positional and velocity measurements. With future updates, particularly with Gaia's final data releases expected in the late 2020s, the uncertainty in timing and distance will shrink even further. This means that within our lifetimes, we'll likely know with incredible clarity exactly when and how close Gliese 710 will come. Already, astronomers are preparing for this knowledge, not because we can do anything to stop the star's approach, but because it offers a unique opportunity. A chance to understand how stellar flybys shape planetary systems, how they affect long-term stability, and how rare or common such encounters might truly be. And though 1.29 million years may seem like an eternity from the perspective of human civilization, from the standpoint of the galaxy, it's the briefest of interludes. A moment's pause. A soon-to-arrive visitor whose shadow already stretches into our future. When speaking of distances in space, the numbers often seem too large to mean anything. A light year. 1 million kilometers. An astronomical unit. These figures blur together, becoming abstract. But in the case of Gliese 710, the projected distance at its closest approach is not just a number, it's a threshold. One that slices deep into the outer defenses of our solar system and crosses into territory rarely touched by any known object, let alone another star. Current models estimate that Gliese 710 will pass somewhere between 10,000 and 20,000 astronomical units, AU, from the Sun. That's still a massive distance. 10,000 Australian dollars is about 1.5 trillion kilometers, but in the architecture of the solar system, this is incredibly close. For comparison, Neptune, the outermost known planet, orbits at just 30 Australian dollars. The Kyper belt, home to Pluto and other icy bodies, stretches out to roughly $50 Australian. The region where Gliese 710 is headed is hundreds of times farther than that, but still well within the gravitational influence of the Sun. This distance places Gliese 710 not just near the Solar System, but deep inside its Oort Cloud, a vast, spherical halo of icy bodies that extends from about $2,000 Australian to potentially $100,000 Australian or more from the Sun. It is thought to be the source of long-period comets, objects that take thousands or even millions of years to complete a single orbit. These ancient ice relics are remnants from the early Solar System, untouched for eons. And they're not gravitationally stable. In fact, they're loosely bound, so much so that even a modest nudge from an outside force can send them tumbling inward. A stellar passage within $20,000 Australian, let alone as close as $10,000 Australian, is not a common occurrence. It represents an intrusion into one of the most distant and undisturbed reservoirs of matter tied to our Sun. Gliese 710's trajectory through this region will be slow and close enough to gravitationally influence vast numbers of these icy bodies. Unlike planets, which are bound tightly to the Sun and require a massive perturbation to shift, these objects are fragile sentinels of the Solar System's periphery, ready to be scattered at the whisper of a passing mass. If Gliese 710 comes as close as the lower estimate, $10,000 Australian, that places it well within the inner Oort Cloud, a region we know very little about because none of its objects have ever been directly observed. Yet even at the higher end of predictions, $20,000 Australian, the encounter still poses a serious gravitational disturbance. The Sun's gravitational dominance in this region is weak. Even small stars like Gliese 710 can temporarily overwhelm it with their own gravitational field when they pass close enough. To understand what kind of gravitational influence this distance implies, consider the concept of the Hill sphere, the region around a body where its gravity dominates over the influence of others. At $10,000 Australian, Gliese 710 will momentarily become a rival to the Sun in the minds of countless icy comets. For many of these ancient bodies, the tug from Gliese 710 may be stronger than the pull of the Sun, redirecting their trajectories completely. But even beyond those that are captured or permanently deflected, the most critical threat lies in what happens to those comets that are merely nudged. A slight alteration in velocity can send a body on a new orbit, one that no longer loops quietly around the Oort Cloud, but plunges inward toward the planets, potentially reaching the inner Solar System thousands or tens of thousands of years later. This is not conjecture. It's a scenario supported by physics, by gravity, and by decades of study into how stellar encounters affect solar systems. In fact, Gliese 710's predicted path is already the closest known approach of any star to our solar system over the next 10 million years, and one of the closest flybys in the history of astronomy. To get a better sense of scale, we might consider another famous near-passer, Scholz's star, which slipped past our solar system about 70,000 years ago. It came within $52,000 Australian, a fraction of Gliese 710's predicted distance, and even then, it may have perturbed some outer Oort Cloud objects. Gliese 710 is expected to pass more than 5 times closer than that. It will not just graze the outer boundary, it will penetrate it. At such a distance, it will likely become one of the brightest stars in the night sky, at least for those future observers, should any exist. During its closest approach, it is projected to reach a brightness of about magnitude -2.7, making it shine as brightly as Mars or Jupiter in today's sky. It won't dominate the heavens, but it will certainly draw attention to anyone who looks up, serving as a brilliant visual warning of the invisible gravitational drama playing out beyond the planets. It's worth noting, too, that $10,000 to $20,000 Australian isn't a fixed boundary. These numbers are built on observational precision, but they are still part of a range. The Gaia data has an extremely small margin of error, but that doesn't mean the actual path won't shift slightly with future refinements. Some more conservative projections suggest a closest pass of around $16,000 Australian. Others, based on different assumptions or less precise data, range from $9,000 to $22,000 Australian. But no matter where within this range the star finally passes, the conclusion remains the same. It's a deep incursion into the Oort Cloud, and it's going to stir things up. So while Gliese 710 will not enter the realm of the planets or come anywhere near Earth in physical terms, its flyby represents one of the most intimate stellar interactions our solar system has experienced, or will experience, in millions of years. And like a passing ghost ship brushing the outer hull of a vessel, it may not leave a mark on the metal, but it may break loose what lies in storage, sending ancient artifacts flying inward to awaken a sleeping world. The Oort Cloud is not something we can see. No telescope, no matter how powerful, has yet directly imaged an object in this vast, distant region. And yet, its existence is one of the most widely accepted features of the solar system. Not because we've observed it, but because the evidence of its influence is written across the night sky, in the icy tails of long-period comets that occasionally dive toward the sun before vanishing again into the void. The Oort Cloud is our solar system's outermost frontier, a spherical shell of frozen time, stretching light years into interstellar space, and Gliese 710 is on a path that will pierce directly into it. First proposed by Dutch astronomer Jan Oort in 1950, the Oort Cloud is thought to be a massive reservoir of icy bodies, cometary nuclei left over from the formation of the solar system. It is believed to extend from about 2,000 Australian dollars from the Sun, just beyond the orbit of the farthest known Kyper belt objects, all the way out to as far as 100,000 Australian dollars, or nearly 1.6 light-years. At those distances, the Sun's gravitational pull is barely strong enough to hold on. The objects in this region are loosely bound, fragile in their orbital allegiance to our star. The Oort Cloud is typically divided into two regions: the inner Oort Cloud, sometimes referred to as the Hills Cloud, which may begin around 2,000 to 20,000 Australian dollars, and the outer Oort Cloud, extending from that range outward into deep space. The inner region is denser though still diffuse, while the outer region becomes progressively thinner and more susceptible to perturbation. These divisions are not strict, but rather conceptual tools to understand the structure of this vast, unseen shell. Despite its invisibility, the fingerprints of the Oort Cloud are everywhere. Long-period comets, those that take more than 200 years to orbit the Sun, are believed to originate from this region. Their orbits are highly elliptical, sometimes plunging in from distances of tens of thousands of AU. Their unpredictable appearances, sudden arrivals, and deep, tilted paths through the solar system all point to origins far beyond the orderly orbits of the planets. They are visitors from the deep freeze, pristine time capsules, unchanged for billions of years. The population of the Oort Cloud is staggering. Some estimates suggest that it could contain trillions of icy bodies larger than 1 kilometer in diameter. These are not massive worlds, but rather frozen remnants, dirty snowballs of rock, dust, and ice left over from the early solar system. They were likely scattered into the distant reaches by the gravitational interactions of the giant planets during the solar system's chaotic youth. What couldn't be ejected entirely into interstellar space became trapped in this spherical shell, held in tenuous orbits where the Sun's grasp is weak, and outside influences, like that of passing stars, can easily tip the scales. That's why Gliese 710 matters. At a predicted distance of 10,000 to 20,000 Australian dollars, it will pass within the very region where the inner Oort Cloud is believed to reside. This is not a distant drive-by. It is an incursion into one of the most gravitationally vulnerable zones in the solar system. The star's gravity, though relatively modest, will be competing with the Sun's in a region where even a subtle tug can alter an object's fate. Cometary bodies that have orbited peacefully for billions of years may find themselves nudged into new, unstable paths, some flung away forever, others sent plunging inward toward the inner solar system. And because the Oort Cloud is spherical, Gliese 710's approach direction matters too. Unlike planetary orbits, which lie mostly in a flat disk called the ecliptic, Oort Cloud objects encircle the Sun in all directions. A star passing through it doesn't just disturb objects in a plane, it can trigger waves of movement from any angle, sending icy missiles from high inclinations or polar orbits, trajectories that our planetary defenses may be poorly suited to monitor. The potential consequence is a comet shower, a long-duration spike in the number of comets entering the inner solar system. Some may merely create beautiful sky shows. Others, depending on size and trajectory, could pose existential threats to Earth. We know from geological history that comet impacts have the power to reshape our planet, triggering mass extinctions, climate shifts, and global upheaval. While most flybys don't result in catastrophic impacts, they increase the probability, a dangerous roll of the cosmic dice. The last suspected major flyby of a star through the Oort Cloud was Scholz's star, which passed within about 52,000 Australian dollars some 70,000 years ago. Even that distant passage may have stirred outer Oort Cloud objects, though any resulting comets would still be thousands of years away from reaching the inner system. Gliese 710, by contrast, will pass more than 5 times closer and through a far denser population of potential projectiles. The gravitational consequences will be significantly more dramatic. But the Oort Cloud is more than just a ticking time bomb. It's a scientific treasure trove. These icy bodies are some of the most primordial material in the solar system, fragments left over from a time before the planets fully formed. If disturbed and sent inward, they offer a chance for study, for insight into the conditions that prevailed over 4.6 billion years ago. Every long-period comet that enters our skies is a messenger from this ancient realm. In a way, Gliese 710's flyby could bring us a gift, the opportunity to study objects we might otherwise never encounter. Still, the uncertainty remains. Because we cannot directly observe the Oort Cloud, we do not know exactly how dense it is, how evenly distributed its objects are, or what percentage of them might be dislodged by a stellar intruder. But we do know from simulation and history that stellar flybys have the power to shake it. And Gliese 710's predicted course will do exactly that. It will not break the solar system. It won't tear the planets from their orbits or ignite some apocalyptic chain reaction. But it will do something subtler, more insidious. It will whisper to the solar system's ancient borderlands. It will rattle the frozen archives of time, disturbing objects that have known nothing but silence for epochs. Some of those objects may drift harmlessly outward. Others may begin slow, spiraling journeys inward, destined to appear in alien skies long after human history has changed or ceased altogether. In that sense, the Oort Cloud is both shield and vulnerability. A protective buffer that also harbors potential threats. A silent halo that may one day speak, when Gliese 710 arrives. Gravity is the great sculptor of the cosmos. It binds stars into galaxies, planets into orbits, and comets into silent loops around stars they may never visit. But gravity is also a source of chaos. It doesn't just hold things in place, it can rearrange, destabilize, even destroy. And when a massive object like Gliese 710 moves close to a region filled with fragile, barely bound material like the Oort Cloud, the gravitational implications are profound. As Gliese 710 enters the outer shell of our solar system, it won't be traveling at breakneck speed like many rogue stars that pass through interstellar space. Instead, it's moving at a relatively gentle pace, about 14 kilometers per second relative to the Sun. That slower speed is deceptive, though. It means Gliese 710 will linger. Its gravitational field will exert influence over a much longer duration than faster stars, giving it more time to interact with, and disturb, the delicate balance of forces at the edge of the solar system. To understand how this works, we must first consider how objects in the Oort Cloud are held in place. These comets and icy fragments orbit the Sun at distances so vast that the Sun's pull on them is feeble. A tiny force, like the passing gravitational field of a star, can nudge these objects off their long-held paths. The Oort Cloud isn't a dense zone. It's a sparse sphere with trillions of objects scattered throughout an enormous volume. Each object is like a speck of dust in an empty cathedral. But if a large figure walks through, even gently, the air it stirs is enough to dislodge the dust. This is what Gliese 710 will do, stir the air, metaphorically. Its gravity will perturb the orbits of Oort Cloud objects through a process known as gravitational tidal interaction. Essentially, this means that the difference in gravitational pull across the cloud, stronger on the side closer to Gliese 710 and weaker on the far side, will stretch and shift the orbits of countless objects. It's a distortion effect that acts across wide areas, influencing not just a single object, but entire swaths of the cloud. These tidal forces can cause several outcomes. Some Oort cloud objects may be ejected entirely from the solar system, their orbits altered so much that they escape the sun's pull and become interstellar wanderers themselves. Others, however, may be nudged inward, their long, circular orbits warped into elongated ellipses that send them diving toward the inner solar system, toward the planets, and potentially, toward Earth. And this won't happen all at once. The gravitational disturbance initiated by Gliese 710 could take tens of thousands to hundreds of thousands of years to fully play out. The objects that are nudged won't appear in our skies the next day or the next century. Instead, a delayed reaction will unfold, a slow cascade of icy bodies migrating inward, some taking millennia to reach the inner system. The initial encounter is the match. The cometary storms that follow are the flames that smolder long after. Astronomical simulations have supported this. Models that replicate the conditions of Gliese 710's future flyby consistently show a significant increase in the flux of comets entering the planetary region of the solar system, particularly those on high inclination and long-period orbits. This would be a stark departure from the current relatively quiet state of the inner solar system, where long-period comets are rare. The effect is sometimes called a comet shower, a temporary surge in the number of these objects, increasing the statistical likelihood of planetary impacts. It's important to note that this gravitational disruption isn't limited to a linear path through the cloud. Because the Oort cloud is spherical, Gliese 710's influence will radiate outward in a three-dimensional field, affecting objects all around its trajectory, not just directly in its path. This adds a level of unpredictability. Some comets may enter the inner solar system from unexpected angles or directions. Others may pass by harmlessly but with orbits altered in ways that make them future threats hundreds of thousands of years down the line. The disruption is also compounded by the star's mass. At around 60% the mass of our Sun, Gliese 710 is substantial enough to create a noticeable gravitational wake as it moves. Not strong enough to tear through the planets or the Sun's core system, but plenty strong enough to reshape the outer boundaries. Imagine dragging a bowling ball through a pond of floating ice. The water won't be disturbed violently, but the movement will send ripples outward. Ice will shift, some pieces will scatter, others will drift inward, bumping and changing paths. That's what this flyby is expected to do, create ripples that spread for eons. And the uncertainty adds another layer of intrigue. While the general range of the flyby is well known, between 10,000 and 20,000 Australian dollars, the exact trajectory, speed, and timing all have slight margins of error. Even small variations in these parameters could lead to significant changes in how many objects are disturbed, how deeply they are perturbed, and what their eventual paths might be. A difference of a few hundred AU closer or farther could mean the difference between a minor cometary ripple and a major shower. Some researchers have modeled best-case and worst-case scenarios. In the best case, Gliese 710 may pass on the higher end of the predicted range and cause only minor disturbances, perhaps a modest uptick in long-period comets, but nothing extraordinary. In the worst-case simulations, if the star passes closer to the 10,000 Australian dollars mark and the cloud is denser than assumed, the inner solar system could face a significant increase in comet activity for 1 million years or more. It's a game of celestial probabilities, played across time spans that defy human comprehension. But the outcome is not purely destructive. In many ways, it is also enlightening. The gravitational disturbance from Gliese 710 could teach us about the density, distribution, and dynamic behavior of the Oort cloud itself, information that has remained elusive for decades. As comet paths shift and more of these ancient bodies come into view, astronomers will have the opportunity to study them, perhaps even visit them with probes in the distant future, unlocking secrets from the dawn of the solar system. Still, the underlying fact remains: Gliese 710 will disturb the Oort cloud. Its gravity will reach across the darkness and pluck at orbits that have remained undisturbed since the Sun was young. Some of those plucks will go unnoticed. Others may echo across time in ways we cannot yet predict. That is the silent power of gravitational disruption, not in the things it tears apart immediately, but in the changes it sets in motion. And once begun, those changes are not so easily undone. In the cosmic stillness of the Oort Cloud, time hardly seems to move. Objects drift in slow, frigid orbits, some taking millions of years to complete a single loop around the Sun. But that tranquility is deceiving. All it takes is a nudge, just the faintest gravitational touch from a passing star like Gliese 710, and the icebound quiet can erupt into motion. What was once stable becomes uncertain. What was once frozen in place begins a journey. And those journeys, multiplied across trillions of icy bodies, may culminate in a surge of comets diving into the inner solar system like arrows loosed from the edge of time. This scenario is not just speculation. It's the logical result of gravitational mechanics, modeled again and again by astronomers who study the evolution of comet populations. When a stellar object moves through or near the Oort cloud, its gravitational influence perturbs the delicate balance that keeps comets in their distant orbits. Some are ejected into deep space, never to return. But many are sent inward, on long, elliptical trajectories that take them across the vastness of the solar system, toward the Sun, the planets, and possibly Earth. The term, comet shower, has often been used to describe the aftermath of such events, but it can be misleading. We're not talking about a sudden, dense bombardment like a meteor storm in the sky. Rather, the result of Gliese 710's intrusion could be a prolonged increase in the number of long-period comets entering the inner solar system over the course of hundreds of thousands, even millions of years. The process is drawn out, like a slow cosmic drumbeat echoing from the outer reaches. Why so slow? Because the Oort cloud is immense, and the distances involved are so vast that even if a comet is nudged today, it may not arrive in the planetary region for tens of thousands of years. And because these orbits are highly elongated, many of the disturbed bodies will swing far into the inner solar system and then back out again, only to return thousands of years later. The result is not a single burst of activity but a sustained increase in comet traffic, drawn from the ancient outskirts by a single stellar touch. Simulations help illustrate this point. Astronomers have used numerical models to estimate how many additional comets might be sent inward following a close stellar flyby like that predicted for Gliese 710. The numbers are startling. Thousands to tens of thousands of new long-period comets could be funneled into the inner system, depending on the exact parameters of the encounter. For comparison, only a handful of long-period comets pass near Earth in a typical year today. A post-flyby scenario might see that rate increase by a factor of 10, 50, or even 100, though spread across millennia. These comets wouldn't arrive all at once, nor in predictable patterns. They would appear at random intervals, from random directions, many on high inclination or retrograde orbits, meaning they would not be restricted to the familiar plane in which the planets orbit. That makes them harder to track and, in some cases, harder to predict. Each one becomes a wild card in the celestial deck, capable of passing harmlessly or striking catastrophically. And therein lies the risk. While most comets are small and would harmlessly burn up in the atmosphere if they entered Earth's path, a small fraction are large enough to cause serious damage, or even planetary-scale destruction. A comet a few kilometers wide, similar in size to the one that likely contributed to the extinction of the dinosaurs, could cause massive environmental upheaval if it impacted Earth. The threat is not constant, but it's elevated during a period of heightened cometary flux. Some researchers have even proposed that mass extinction events on Earth may have been linked to past stellar flybys that disturbed the Oort cloud. While evidence for direct causation is still debated, the timing of certain extinction pulses and spikes in comet activity do appear to coincide. It's possible that Earth's history has already been shaped in part by the silent influence of long-gone stars. But it's not all doom and destruction. Comets also bring opportunity. They are carriers of the early solar system's raw material, ice, dust, organics. Some theories even suggest that Earth's water may have been delivered in part by comet impacts during the planet's early bombardment phases. A future increase in comet activity might offer scientific treasure, a chance to study these ancient bodies up close, perhaps even harvest them for resources if human civilization endures long enough to develop the technology. That's the strange duality of a comet surge. It's a potential threat, yes, but also a delivery of knowledge. A window into the past and a challenge to the future. If Gliese 710's flyby sends a torrent of icy visitors toward us, it may one day force humanity, if still present, to confront the fragility of its place in the cosmos, to look skyward not just in wonder, but in vigilance. Astronomers are already preparing. Surveys like Pan-STARRS and the Vera C. Rubin Observatory's LSST are designed in part to detect moving objects in the sky, asteroids and comets alike. Future generations of these surveys will likely monitor comet influx in greater detail, perhaps even tracing specific waves of activity back to events like the Gliese 710 flyby. The data could reveal patterns, allowing astronomers to map the chain of cosmic cause and effect stretching from a star's passage to a comet's arrival. But no telescope can stop the comets from coming. They are already on their way, in a sense, triggered by gravitational seeds not yet sown. When Gliese 710 enters the Oort Cloud, it will plant millions of those seeds. And over time, they will bloom into icy arcs in the night sky, silent, beautiful, and potentially deadly. That's the paradox of this future event. It won't bring fire. It won't bring light. It will bring motion, a long, slow unraveling of frozen paths, a surge of comets awakened from their ancient sleep, and a reminder that in space, even the gentlest touch can echo for eons. The universe is vast and ancient, and yet it has a way of narrowing its gaze on the smallest, most vulnerable corners. Earth, a speck in a cosmic ocean, has been struck before, and it will be struck again. The forces that govern the heavens care nothing for the timeline of civilizations. And so, when we speak of the odds of Earth being hit by a comet disturbed by Gliese 710's future flyby, we're not dealing in drama or science fiction. We're dealing in probabilities, cold, mathematical, and indifferent. To understand the risk, we need to begin by examining the normal background rate of cometary impacts. Long-period comets, the kind likely to be dislodged by Gliese 710's gravitational influence, currently pass through the inner solar system only rarely. On average, about 5 to 10 long-period comets per year are detected near the Sun. Most pose no threat to Earth. They come and go on paths that take them far above or below our orbital plane. And they are, by the time they arrive, relatively sparse, culled by billions of years of natural selection in the gravity field of the Sun. But that's the background noise, the quiet hum of a stable system. The story changes when a star like Gliese 710 comes barreling through the Oort Cloud. Simulations suggest that such a flyby could increase the influx of comets into the inner solar system by a factor of 10 to 100 over a period that could last several million years. It won't happen all at once. The rise will be gradual, and the peak in comet activity may come a million years or more after the closest approach. But it will come. Now let's talk numbers. If the baseline long-period comet rate is about 5 to 10 per year, and Gliese 710 increases that rate by a factor of 100, we could be facing hundreds of comet encounters per year during the most active phase. Not all of these will be Earth-crossers, of course. The inner solar system is a wide and mostly empty place. The orbits of comets are chaotic, and most will miss all planets entirely. But when the numbers go up, so does the risk. Historically, Earth-impacting comets are extremely rare. The last confirmed large-scale impact of a long-period comet is uncertain. Most large craters on Earth are attributed to asteroids, not comets. That's not because comets are harmless, but because long-period comets are harder to detect, less frequent, and statistically less likely to strike. Their orbits are longer, their paths more erratic, and their velocities when entering the inner system are far higher, making any potential impact all the more devastating. A comet on a collision course with Earth would likely be moving at 50 to 70 km/s, nearly double the speed of most Earth-crossing asteroids. That means far more kinetic energy per unit mass. Even a relatively small comet, say 1 to 2 kilometers wide, could release energy equivalent to millions of megatons of TNT, far beyond anything ever witnessed by human civilization. So, what's the real risk? Based on various studies, the probability of a long-period comet impacting Earth in any given year under normal conditions is estimated at roughly 1 in 50 million. If Gliese 710 increases the population of such comets by a factor of 100, then that risk could spike to 1 in 500,000 during the peak period. Still low, but no longer negligible, especially over geological timescales. Over the course of the entire comet shower era, which may last several million years, the cumulative probability of at least one major Earth impact becomes significant, possibly approaching or exceeding 50% in some models, depending on assumptions about the number, size, and orbital dynamics of the affected comets. And here's where the threat becomes existential. Unlike asteroids, which mostly orbit in or near the ecliptic and can be catalogued and monitored with relative ease, long-period comets are often discovered only months or even weeks before they reach perihelion, their closest approach to the Sun. By the time we see them, it may be too late to deflect or mitigate a collision. Their long, unpredictable orbits, combined with their high approach speeds, make them among the hardest cosmic threats to deal with. Even a modest impactor, say, a 500-meter-wide comet, could cause regional devastation on a continental scale. An object 1 to 2 kilometers wide could result in global effects, including massive tsunamis, global wildfires, temperature drops, and the collapse of ecosystems. A larger comet, 5 kilometers or more, would very likely cause a mass extinction event, rivaling or exceeding the Chicxulub impact that contributed to the extinction of the dinosaurs. There's also the question of secondary impacts. Gliese 710's flyby won't trigger just one comet. It will likely send waves of them inward, some missing Earth, others not. Some may fragment as they approach the Sun, sending multiple smaller pieces along similar paths. This has been observed before. The Shoemaker, Levy 9 comet, which broke into 21 fragments and slammed into Jupiter in 1994, was a vivid reminder of what a fragmented comet can do. If such a shattered object were headed toward Earth, it might cause multiple impacts over a span of days or weeks, enough to overwhelm any conceivable defense. Could humanity survive such an event? Possibly. But not without great loss. The infrastructure of civilization is fragile, and the atmospheric and ecological consequences of a major impact would be global, not local. The challenge wouldn't just be surviving the initial strike, it would be enduring the years of aftermath, failed crops, poisoned oceans, ash-darkened skies. So are we doomed? No. But the risk is real. It is not imminent, and it may never come to pass. Gliese 710 may cause only a modest spike in cometary activity. But it could cause more. And it is the possibility of that outcome, not the certainty, that demands attention. Today's astronomers are aware of this. Efforts are underway to better map long-period comet dynamics, to refine models of Oort Cloud evolution, and to improve our detection of inbound objects. But there is no current system capable of offering more than a few months' warning for a long-period comet on a direct trajectory toward Earth. In the end, Gliese 710's flyby is a reminder of cosmic humility. It may not affect us in our lifetime, or in the lifetime of our civilization. But Earth's history spans billions of years, and its future may span billions more. A 1 in a million event in a single year becomes a near certainty over geological time. And so we look to the stars, not just in wonder, but in preparation. For a quiet star is coming, and behind it may follow a rain of ice and fire. The notion of a star like Gliese 710 disturbing the outer edges of our solar system may sound like a distant, almost cinematic event, a once-in-a-universe anomaly. But in reality, the cosmos is not a still place. Stars are in motion, including our Sun, and as they drift and orbit the galactic center, they occasionally come close to one another. These flybys aren't common in a human lifetime, but over millions of years, they become almost inevitable. In fact, we now know that stellar encounters have happened before, some of them much more recently than you might think, and others potentially leaving their fingerprints on Earth's geological and biological history. The most famous and well-documented stellar flyby in recent history is that of Scholz's star. Roughly 70,000 years ago, this dim, binary system, comprising a red dwarf and a brown dwarf, passed within about 52,000 astronomical units, AU, of the Sun. That's about 0.8 light-years, which may sound far, but it's well within the outer Oort cloud. At the time of its closest approach, Scholz's star likely shone dimly in the night sky, just on the edge of naked eye visibility, assuming anyone on Earth noticed. Our species, Homo sapiens, was alive then, possibly even looking at it without understanding what it was. What's fascinating is that Scholz's star wasn't detected until 2015. Its proximity was inferred through the measurement of stellar motion, specifically, radial velocity and proper motion data. By retracing its path, astronomers realized that this small, faint object had once been the closest known interstellar visitor in modern history. And while its passage didn't seem to result in any major cometary storms, it did enter the outskirts of the Oort cloud. Some researchers even speculate that a few long-period comets appearing in our skies today might trace their perturbed orbits to this ancient passage. Go further back, and the waters become murkier, but no less intriguing. There is evidence, though not yet conclusive, that other stellar flybys may have occurred millions of years ago and may have had far more dramatic consequences. Some scientists propose that mass extinction events, including the one that ended the reign of the dinosaurs, might have been triggered or influenced by an uptick in cometary activity following such close encounters. These are difficult theories to prove, because the geological record blurs with time, and the motions of stars become harder to reconstruct the further back you go. Still, some intriguing clues exist. One of them involves the Nemesis hypothesis, a controversial but captivating idea proposed in the 1980s. The theory suggested that our Sun might have a distant, dim companion star in a long, elliptical orbit, taking tens of millions of years to complete one revolution. This hypothetical star, dubbed Nemesis, was thought to pass through the Oort cloud every 26 million years or so, disturbing comets and triggering extinction events on Earth. The idea was inspired by apparent periodicity in Earth's mass extinctions, but over time, Nemesis has fallen out of favor due to a lack of direct evidence. No such companion has been detected, even with extensive sky surveys. However, the idea behind Nemesis, namely, that comet showers can be triggered by stellar influence, remains solid. We don't need a dark companion star to explain these phenomena. The Milky Way is teeming with stars, and over the lifetime of our solar system, the Sun has likely had dozens of near passes with other stars, many of them unrecorded by human eyes, but not by their effects. One tantalizing line of evidence comes from studies of impact craters and isotope layers in the geologic record. Some researchers have identified patterns in these data that suggest clusters of impacts spaced tens of millions of years apart. While controversial, one possible explanation is the periodic influx of comets from the Oort cloud, triggered by the gravitational nudges of passing stars or galactic tides as the solar system moves through the plane of the Milky Way. Even without relying on controversial hypotheses, the simple fact remains: stellar flybys are a natural part of the solar system's life. We know that over the last few billion years, stars have come and gone, some closer than others. While the Sun is currently moving through a relatively sparse region of the galaxy known as the local bubble, it hasn't always been this isolated. Earlier in its life, the Sun may have passed through dense molecular clouds or star clusters where close encounters were more frequent. During those eras, it's entirely plausible that massive perturbations in the Oort cloud, and even intersolar system chaos, could have been sparked by nearby stars. In fact, one study from 2018 analyzed the data from the Gaia mission and compiled a list of stars that are predicted to pass within 1 parsec, 206,000 AU, of the Sun over the next few million years. Dozens of stars were identified, but Gliese 710 stands out as the closest predicted flyby. None of the others comes nearly as close or as slowly, which makes Gliese 710 an unusually disruptive visitor, but not a completely unprecedented one. It's even possible that the Sun itself, when it formed 4.6 billion years ago, was born in a stellar nursery where nearby stars came close enough to sculpt the early solar system. Some astronomers believe the sharp outer edge of the Kyper belt, around $50 Australian, might be a fossil relic of such an early stellar encounter, which gravitationally pruned the disk of planetesimals in our young system. Taken together, the history of stellar flybys is not a story of catastrophe after catastrophe. Rather, it's a long, slow rhythm, an ancient pattern of celestial choreography, where stars drift close, disturb a few things, and then pass on. Most encounters do little. Some stir the deep cloud of comets. A rare few, perhaps 1 in 100 million, might cause a cascade of events that ultimately alters life on Earth. So when we look ahead to Glee 710's future visit, we are not facing a singular event but a familiar cosmic chapter, one that has played out before and will play out again. The solar system is not an island. It is part of a bustling galactic sea, and occasionally other ships drift close. They don't always collide, but their passing wakes can leave ripples that reach the very shores of our world. When we look up at the night sky, we see stars as fixed beacons of light, seemingly frozen in place. But in truth, those stars are anything but still. Each one is in motion, spiraling, drifting, orbiting the galactic center like grains of dust caught in a vast celestial whirlpool. To the naked eye, these motions unfold far too slowly to perceive. But with the right instruments, and the right data, we can peel back the curtain of time and witness an astonishing reality. Stars are travelers. And some, like Glee 710, are heading directly for us. The question is, how do we know this? The answer lies in one of the most ambitious and precise space missions ever launched, Gaia, the European Space Agency's revolutionary observatory designed to chart the three-dimensional positions, motions, and characteristics of over 1 billion stars in our galaxy. Launched in 2013, Gaia orbits at the L2 Lagrange point, about 1.5 million kilometers from Earth, where it observes the sky with a level of precision that was, until recently, impossible. Gaia's purpose is to create a complete and dynamic map of the Milky Way. Not just a snapshot of where stars are now, but a full movie of where they were, where they are going, and how fast they're getting there. Using an astrometric technique, essentially measuring tiny shifts in a star's position over time, Gaia can determine the proper motion of stars with extraordinary accuracy. In addition, by analyzing the Doppler shift in the light of each star, Gaia measures radial velocity, how fast a star is moving toward or away from us. Combine these two measurements, and you get a complete 3D velocity vector for each star. But that's only part of the equation. To predict where a star will go in the future, you need to integrate that data with models of galactic motion, calculations that consider the gravitational effects of the Milky Way's disk, bulge, dark matter halo, and local star clusters. It's an enormous computational task, but one Gaia is uniquely suited for. With its precise star positions and velocities, astronomers can roll the clock forward or backward, calculating past encounters and future flybys with stunning precision. This is how Glee 710 entered the spotlight. Prior to Gaia, the idea that Glee 710 might pass near our solar system had already been floated based on earlier measurements from the Hipparcos satellite and other ground-based telescopes. But those measurements came with wide margins of error. We knew Glee 710 was moving in our general direction, but how close it would actually come was uncertain, perhaps within a few light years, or perhaps far enough to be inconsequential. Then came Gaia. With the release of Gaia DR2, Data Release 2, in 2018, astronomers gained access to far more accurate measurements of Glee 710's motion. A team of researchers led by Piotr Dudzinski and Filip Bursky reanalyzed its trajectory using this new data. The result was astonishing and sobering. They found that Glee 710 was on a near-certain course to pass within 10,000 to 20,000 Australian dollars of the Sun, well within the outer boundary of the Oort Cloud. Even more startling, they calculated that the encounter would occur in about 1.29 million years, give or take a few tens of thousands of years. This wasn't a guess. It was based on detailed integration of motion, applying Newtonian and relativistic gravitational models to both the Sun and Glee 710, treating them not as fixed points, but as moving bodies orbiting within the dynamic gravitational field of the Milky Way. The researchers simulated the star's future position hundreds of thousands of times, incorporating small uncertainties in its current location and speed. And across these simulations, one result was consistent: Gliese 710 is on track for a very close flyby. Even more recently, Gaia's EDR3, Early Data Release 3, and later releases have further refined the star's path. As measurements get more precise and the baseline of observation lengthens, giving Gaia more time to detect changes in motion, the uncertainty in Gliese 710's predicted trajectory shrinks. With each update, the scenario becomes clearer, not murkier. All current data converges on a singular narrative: a close approach is inevitable. But what gives us such confidence? The key lies in the nature of astrometric data. Gaia doesn't just take snapshots, it builds motion profiles. Over the course of years, it tracks how stars drift relative to each other across the sky, detecting changes on the order of microarcseconds, fractions of a fraction of a degree. To put that in perspective, Gaia can measure the width of a human hair from 1,000 kilometers away. This level of precision allows astronomers to detect the very slightest shift in a star's apparent position and to determine how that shift changes over time. From there, we apply what we know about gravity. The Sun and Gliese 710 both orbit the galactic center at roughly 220 kilometers per second, but not in perfect harmony. Their orbits wobble, respond to the galaxy's mass distribution, and evolve over time. Using high-fidelity galactic models that account for these motions, astronomers simulate their trajectories across millions of years. When paths converge, when a star's future motion intersects the Sun's location, we take notice. Of course, there are still uncertainties. Even with Gaia's unparalleled precision, we cannot know the exact mass of Gliese 710 down to the gram. Small differences in the star's mass, or tiny perturbations from other stars or dark matter clumps, can influence its ultimate trajectory. But the error bars are small. Current models place the minimum distance of the flyby at 10,000 Australian dollars with a 90% confidence interval, and most simulations fall within the range of 10,000 to 20,000 Australian dollars. That level of certainty is astonishing. We can't predict the weather next month with confidence, but we can predict a stellar encounter over 1,000,000 years in the future with remarkable clarity. That's the power of precision astrometry. That's the legacy of Gaia. And this isn't a one-off success. Thanks to Gaia, astronomers have already catalogued dozens of stars that will pass within 1 parsec, about 206,000 Australian dollars, of the Sun in the next few million years. Most are harmless, flybys at safe distances. But Gliese 710 stands apart, not because it's massive or bright, but because its trajectory and velocity make it the closest and slowest stellar encounter known in the foreseeable future. The slowness matters too, because it means its gravitational influence will be stronger and longer lasting, especially in the sensitive outer zones of the Oort Cloud. Gaia has not only shown us this future, it's given us a timeline. It's told us when to expect the first disturbances, how long the cometary influx might last, and how likely we are to experience secondary effects. The data also provides a foundation for future missions and surveys, tools that may one day track the earliest comets arriving as a result of the flyby, thousands of years before the star itself appears in our sky. It's poetic in a way. A spacecraft orbiting quietly around our tiny planet has looked across light years and centuries to warn us of a visitor we'll never meet, but that our distant descendants might. It is a reminder of what we can achieve when we combine technology, curiosity, and patience, and a lesson in how small, precise observations can reveal grand cosmic stories. And the story of Gliese 710 is still unfolding. In the grand tradition of celestial cartographers, from ancient star watchers to telescope pioneers, few instruments have reshaped our understanding of the galaxy as profoundly as the Gaia Space Observatory. A mission of staggering ambition and meticulous precision, Gaia has elevated astrometry, the measurement of star positions and motions, to an art form. It is not just a telescope, it is a time machine, a galactic surveyor, and perhaps most crucially, a sentinel that has brought distant threats like Gliese 710 into focus with breathtaking clarity. Launched by the European Space Agency, ESA, on December 19, 2013, Gaia resides in a quiet gravitational haven, Lagrange point 2, L2, about 1.5 million kilometers from Earth, where the gravitational pull of Earth and the Sun are balanced. There, Gaia operates in a slow, stable orbit around the Sun, shielded from thermal and mechanical disruptions that could otherwise compromise its measurements. Its mission: to chart a three-dimensional map of the Milky Way, tracking over 1 billion stars with microarc-second precision. To appreciate Gaia's role in identifying Gliese 710's path, we must first understand the core of what Gaia does. Astrometry may seem like an abstract pursuit, measuring positions of stars, but it is the foundation of celestial mechanics. Without it, we cannot determine orbits, velocities, or trajectories. Gaia refines this art to a degree never before achieved. Its measurements are so precise that it can detect the slight wobble of a star caused by the gravitational tug of an orbiting planet, or the minuscule drift of a star across the sky over the course of years. For a star like Gliese 710, this means Gaia can measure its exact position in the sky at multiple epochs, its parallax, which reveals its distance from Earth, its proper motion, or the sideways movement across the sky, its radial velocity, or how fast it is moving toward or away from us. All of this data comes together to build a six-dimensional map of Gliese 710's location and velocity vector in space. With those 6 parameters, 3 for position, 3 for motion, scientists can simulate the star's past and future path with astonishing accuracy. For Gliese 710, this has allowed researchers to determine not only that it is headed toward our solar system, but exactly how close it will get, and when. Gaia's contribution didn't just clarify the picture, it rewrote it. Before Gaia, estimates of Gliese 710's closest approach were rough and riddled with uncertainty. Earlier data, such as from ESA's Hipparcos mission, Gaia's predecessor, hinted at a possible encounter, but error margins were too large to draw confident conclusions. With the release of Gaia Data Release 2, DR2, in 2018, that uncertainty vanished. The new data showed, with statistical robustness, that Gliese 710 will pass within about 10,000 to 20,000 astronomical units, AU, of the Sun in 1.29 million years, firmly within the Oort Cloud. And Gaia didn't stop there. Its later releases, EDR3 in 2020 and DR3 in 2022, have continued to refine those measurements. Each new data point acts like another frame in a slow-motion film of Gliese 710's journey. With each additional year of observation, Gaia reduces the margin of error in our predictions, like tightening the focus on a distant ship approaching from the horizon. But why is this precision so vital? Because small errors in a star's position or speed can translate into huge uncertainties over million-year timescales. If Gaia were off by even a fraction of a percent in Gliese 710's radial velocity or trajectory, the estimated closest approach distance could vary by thousands of AU. That's the difference between a harmless passage on the edge of the Oort Cloud and a flyby close enough to wreak havoc throughout the solar system. By bringing those uncertainties down to a manageable range, Gaia has made Gliese 710's predicted flyby one of the most confidently modeled stellar encounters in the history of astronomy. And it doesn't end with Gliese 710. Gaia has catalogued dozens of other stars with close approaches projected over the next 10 million years. Most of them are far less dramatic, passing tens or hundreds of thousands of AU from the Sun, too distant to significantly perturb the Oort Cloud. But only because of Gaia do we know this. Without its data, we would be flying blind through the galaxy, unaware of which stars are drifting nearby, which ones are passing quietly, and which, like Gliese 710, might whisper chaos into our future skies. What makes Gaia so revolutionary is its all-sky, long-term coverage. Unlike observatories that target specific stars or regions, Gaia scans the entire sky repeatedly, measuring positions and motions again and again over time. This repeated scanning is what gives it the power to detect subtle accelerations and changes in motion, key to understanding gravitational interactions. Gaia's observations are then matched with sophisticated computational models. Astronomers feed the raw data into orbital integration software, taking into account the gravitational potential of the Milky Way, the influence of dark matter, and the solar system's own peculiar motion. They run hundreds of thousands of simulations, each with slight variations in the initial conditions, to produce a statistical cloud of possible futures. For Gliese 710, the vast majority of simulations cluster tightly around the same outcome, a close passage deep into the Oort Cloud. This convergence is Gaia's gift. It allows us to plan, to speculate, to wonder, not from a place of ignorance, but from knowledge. And it's worth pausing to recognize the scale of Gaia's achievement. By tracking the movements of stars across light years of distance, Gaia is effectively doing interstellar traffic control, mapping which stars might cross our path millions of years in advance. It's as if we could detect a tiny pebble thrown across a football field, determine its arc, and predict exactly where it will land a decade from now. In the story of Gliese 710, Gaia is not just the narrator, it is the discoverer, the analyst, the alarm bell, and the cartographer. Without it, we would still be blind to the star's approach, and unaware of the cometary consequences that might follow. With it, we are given a warning, not of doom, but of the cosmic inevitabilities that shape the fate of solar systems. Thanks to Gaia, Gliese 710 is not a nameless visitor from the dark. It is a known quantity, a star with a name, a trajectory, and a role to play in our solar system's future. Its story is no longer hidden. It's written in data, traced in algorithms, and watched with growing fascination by astronomers across the globe. Gaia has shown us the future. What we choose to do with that knowledge is up to us. In the delicate art of celestial prediction, precision is power, but so too is humility. For all the breakthroughs brought by Gaia, and for all the confidence we have in Gliese 710's approaching path, the universe still dances with uncertainty. Even the best data carries with it a whisper of chaos. That whisper becomes louder the further forward we look in time, and when we peer 1.29 million years into the future, it is not a single line we see, but a tapestry of possible outcomes, woven from variations in distance, speed, mass, and the complex gravitational fabric of the Milky Way. To truly understand the nature of Gliese 710's predicted flyby, we must first grasp the kinds of uncertainties that matter, and how even microscopic differences today can ripple into dramatically different scenarios over cosmic timescales. These uncertainties are not signs of failure. They are the natural consequence of working with vast distances, moving targets, and a galaxy filled with unseen mass. Let's begin with distance, specifically, the current distance between us and Gliese 710. Thanks to Gaia's exquisite parallax measurements, we know this distance with high precision. As of the latest data releases, Gliese 710 is roughly 62 light-years away, or about 19 parsecs. But parallax, though powerful, is not infallible. A margin of error of just a few milliarc-seconds in Gaia's readings can lead to an error of dozens of AU in the projected closest approach. For context, remember that $1, the average distance between Earth and the Sun, is about 150 million kilometers. An error of just $1,000 in Gliese 710's approach could mean the difference between a relatively safe flyby at the edge of the Oort Cloud, and one that punches straight through its dense inner core, vastly increasing the gravitational impact on its icy inhabitants. Next comes speed, both radial velocity and tangential, or proper, motion. Radial velocity is the rate at which Gliese 710 is approaching or receding from us, measured via the Doppler shift in its spectral lines. A redshift indicates the star is moving away, a blue shift shows it's coming closer. Current estimates place Gliese 710's radial velocity at around -14 km/s, indicating it is moving toward the solar system. But again, there's a margin of error here, typically a fraction of a kilometer per second. That may sound small, but over 1 million years, it becomes significant. Tangential velocity, the sideways motion of the star across the sky, is measured from Gaia's long-term tracking of its position. While Gaia's accuracy in this regard is unrivaled, uncertainty still exists due to factors like observational noise, calibration errors, or temporary lensing effects from intervening matter. A tangential speed error of even 0.1 km per second can cause Gliese 710's projected path to shift by thousands of AU over the course of 1.29 million years. This means the star could pass closer, or farther, than we currently expect. But there is another layer of uncertainty that is often less discussed: mass. Specifically, the mass of Gliese 710 itself. As an orange dwarf star, it is smaller and less massive than our Sun, with a mass estimated to be about 0.6 times that of the Sun. But that figure is based on models, spectral data, brightness, and temperature, not direct measurement. A slight underestimation or overestimation in the star's mass means a change in how strongly it will pull on the surrounding Oort cloud objects as it passes by. If Gliese 710 is more massive than expected, its gravitational influence will be greater, and the number of comets it dislodges could increase. If it is less massive, its passage might be quieter, resulting in a gentler stirring of the outer solar system. Likewise, if the star has unseen companions, a planet, a brown dwarf, or even another star in a wide orbit, those companions could either amplify or diminish the net gravitational effects depending on their configuration. Even more subtle is the uncertainty in the gravitational environment of the galaxy itself. The Sun and Gliese 710 are not moving through a vacuum. They are orbiting the galactic center at over 200 kilometers per second, influenced by the gravitational pull of stars, gas clouds, and especially the dark matter halo that envelopes the Milky Way. Small deviations in the local gravitational field, caused by passing stars, molecular clouds, or unseen dark matter clumps, can slightly deflect the trajectory of either the Sun or Gliese 710 over millions of years. These deflections are incredibly hard to model, and yet they can accumulate over time. To manage these uncertainties, scientists don't just run a single simulation. They run tens of thousands of simulations, each one with slightly different starting values based on the full range of Gaia's data errors. These simulations produce a probability distribution of outcomes. Instead of declaring a single definitive closest approach distance, astronomers can say something like, "There is a 90% probability that Gliese 710 will pass between 10,000 and 20,000 Australian dollars from the Sun." And that's the current consensus. Most models cluster tightly around 13,000 Australian dollars, but outliers exist. A small percentage of simulations place the star as close as 8,000 Australian dollars, and a few as far as 22,000 Australian dollars. The bulk of scenarios, however, lie comfortably inside the Oort Cloud's outer region, and well outside the planetary zone, which ends around 30 to 50 AU from the Sun. So while Gliese 710 is not expected to pose a direct gravitational threat to the planets or the Sun, its impact on the Oort Cloud is very likely. It's also worth considering how these uncertainties might evolve in the future. Gaia continues to collect data, and each new release improves the baseline, the length of time over which star motions have been measured. A longer baseline means smaller errors, which means more reliable trajectory forecasts. Upcoming data releases, especially the full DR4 and beyond, will likely reduce the margins of error in Gliese 710's path even further, possibly by an order of magnitude. Additionally, complementary observations from other missions, such as ground-based spectrographs and future space telescopes like the Nancy Grace Roman Space Telescope, could help refine our understanding of Gliese 710's mass and composition. If an exoplanet is discovered around Gliese 710, for example, it could alter the dynamics of the flyby or offer new clues about the star's gravitational profile. In the end, refining the numbers is not about removing all uncertainty. That's impossible. The nature of chaotic systems means that tiny changes now can grow into large consequences later. But it is about narrowing the window, reducing the possibilities to a well-understood range, and preparing for all realistic outcomes. For Gliese 710, that preparation means understanding the full spread of its potential effects, from a mild increase in comet activity to a dramatic spike that could reshape the face of the inner solar system. It means watching the sky, not with fear, but with a commitment to clarity and foresight. Science cannot predict the future with perfect certainty, but with missions like Gaia and the work of thousands of astronomers around the world, it can give us something almost as powerful, a glimpse. A glance through time, based on light, gravity, and reason. Although current models strongly suggest that Gliese 710 will pass at a relatively safe distance, somewhere between 10,000 and 20,000 astronomical units (AU) from the Sun, well beyond the orbits of our planets and even deep within the Oort Cloud, science is never about absolutes. It's about probabilities, and within every probability distribution lies the edge of possibility. That leads us to a more provocative and unsettling question. Could Gliese 710 come even closer than we expect, close enough to stir the Kyper belt, destabilize planetary orbits, or worse, graze the outer edge of the solar system's heart? To even entertain this scenario, we must understand the fragility of long-term predictions. Astronomical forecasting is much like meteorology, but stretched across millions of years. Slight deviations in a star's current velocity, its mass, or the gravitational interference from nearby galactic bodies can amplify over time. A change of just 0.1 kilometers per second in velocity, when extrapolated across 1.29 million years, can shift Gliese 710's future position by thousands of AU. While our current best estimates place its closest approach near 13,000 Australian dollars, there exists a tail end in the distribution of simulations, rare but statistically plausible, that allow for a significantly closer encounter. In a small fraction of these scenarios, on the order of less than 1%, Gliese 710's path could thread through the inner edge of the Oort Cloud and approach as close as 5,000 Australian dollars. At this range, it would not only disturb long-period comets but also potentially influence trans-Neptunian objects, especially those in the scattered disk region of the Kyper belt. Some simulations, more speculative in nature, have even explored flybys within 1,000 Australian dollars, though these fall well outside the 90% confidence interval provided by Gaia's latest data. Still, the possibility cannot be entirely excluded, not because the data is wrong, but because the universe has many variables we have not yet measured. To envision Gliese 710 crossing into the planetary zone, however, that is, within 50 Australian dollars of the Sun, requires a dramatic deviation from current predictions. Such a scenario would be extraordinary, involving either a substantial error in our understanding of its present trajectory or an unexpected gravitational perturbation en route. For example, imagine Gliese 710 encounters a massive, unseen object, a dark matter clump, a rogue planet, or another star, during its journey. Even a slight deflection could, in theory, change its course over 1 million years by just enough to nudge it inward. There is also the question of measurement bias or unknown companions. While Gaia has mapped Gliese 710's motion to exquisite detail, it's not inconceivable that the star could harbor a faint, wide-orbiting companion, like a brown dwarf or rogue planet, that hasn't been detected. If such a companion exists and is positioned just right, its gravitational pull could subtly alter the system's barycenter, center of mass, causing our models of Gliese 710's trajectory to be slightly off. Over time, this discrepancy could accumulate into something larger, drawing the star closer to the Sun than currently forecasted. To reach the planetary region, Gliese 710 would have to pass through the Kyper belt, a wide, icy disk extending from about 30 to 50 Australian dollars. A flyby inside this zone would likely be catastrophic, not for the planets themselves, which are tightly bound to the Sun, but for the thousands of small icy bodies populating this distant region. These objects, already only marginally stable, could be tossed into erratic orbits, some falling inward toward the Sun, others flung out into interstellar space. The resulting chaos might send an unprecedented surge of comets inward, far greater than any standard Oort Cloud disruption. And should Gliese 710 pass even closer, say within 20 Australian dollars, its gravity could begin to influence objects in the inner solar system. What would such a close flyby look like from Earth? If Gliese 710 came within even 1,000 Australian dollars of the Sun, it would become easily visible to the naked eye, potentially outshining Sirius in the night sky. A flyby at 100 Australian dollars would make it appear like a brilliant orange star, slowly migrating across the heavens over decades. And if it entered the planetary zone, say, within 50 Australian dollars, it would become one of the brightest objects in the sky after the Sun and Moon, casting a strange new light over Earth's nights for centuries. But the real danger would be gravitational, not luminous. Inside $100, Gliese 710's gravity could perturb the orbits of outer planets, especially Neptune and Uranus. While these planets are not easy to destabilize, a close enough encounter could cause orbital shifts of a few degrees, sufficient to alter long-term stability. Over thousands of years, that could trickle inward, subtly affecting the orbits of Jupiter, Saturn, and eventually even Earth. It would be a slow-motion destabilization, taking eons to fully manifest, but with potentially irreversible consequences for the solar system's architecture. Could Earth itself be at risk in such an ultra-close encounter? Direct ejection is unlikely unless Gliese 710 passes within $20 or less, which current data rules out. But indirect effects, like triggering a heavy bombardment of comets, are very much in play. A close flyby could unbind countless icy bodies, converting them into sunbound missiles. Many would miss. Some wouldn't. Earth, already scarred by past impacts, could see a rise in extinction-level threats. Even more speculative is the idea that such a flyby could pull objects from our solar system into its own gravitational sphere, effectively stealing some of our comets or Kyper belt objects. If Gliese 710 had planets, or formed them after capture, it's possible that in a billion years, those worlds could harbor ancient solar system relics. Stranger things have happened in the cosmos. Still, let's return to probabilities. Based on current data from Gaia, a passage within $10,000 to $20,000 is by far the most likely scenario. A flyby within $5,000 is very unlikely. And one within $1,000, or inside the planetary zone, is exceedingly rare, with less than a 1 in a million chance under current models. But even that tiny possibility has a gravitational weight of its own, pulling at our imagination, reminding us how thin the boundary is between expected and extraordinary in a galaxy governed by chaos. The universe is filled with near misses, invisible threads of fate that only become visible in hindsight. Gliese 710 is one of them, a cosmic traveler on a million-year journey toward our neighborhood. It may pass quietly, disturbing only the icy outlands of the Oort Cloud. Or, in some low-probability, high-impact twist of gravitational fate, it may venture closer, turning the night sky brighter, the Kyper belt wilder, and the future of the solar system more unpredictable than any of us imagined. Even though Gliese 710's projected trajectory keeps it well beyond the planetary zone, its potential to influence the Kyper belt, the frigid, distant realm of icy debris beyond Neptune, remains a serious consideration. While not as vulnerable as the loosely bound Oort Cloud, the Kyper belt is still gravitationally delicate. Its population of dwarf planets, minor bodies, and frozen leftovers from the solar system's formation sit in an orbital limbo, tenuous, thinly spread, and only moderately anchored to the sun's grip. The arrival of an interstellar visitor, even at tens of thousands of AU, can create ripples here, sometimes subtle, sometimes profound. The Kyper belt extends from approximately $30 to $50 from the Sun, with its outer boundary blending into what's known as the scattered disk, a region of erratically orbiting icy bodies that stretches out much farther, up to $100 and beyond. The objects here are not tightly clustered, they're sparse and spread out, orbiting with inclinations and eccentricities that vary wildly. Some have perihelia close to Neptune, others swing out on distant loops influenced by long-past gravitational encounters. This is not a static region, it is a zone of quiet chaos. So how would Gliese 710's flyby affect it? To answer that, we need to revisit the projected closest approach distance, around $13,000, based on Gaia's current data. That's well beyond the far edge of the scattered disk. However, gravitational influence is not binary. It doesn't simply turn on at $1,000 and off at 10,000. Like tides from the moon affecting Earth's oceans, stellar gravitational fields diminish gradually with distance, but can still exert cumulative effects over time. For a star like Gliese 710, even at $13,000, the tidal forces it exerts across the solar system can produce slight but meaningful orbital perturbations, especially in the outermost bodies. Simulations of similar stellar encounters have shown that objects with high eccentricities or inclined orbits are particularly susceptible to disruption. A passing star's gravity doesn't just tug uniformly. It can twist and torque orbits, increase eccentricity, and nudge objects into new paths. These perturbations could cause some Kuiper belt objects to become unstable, leading them to migrate inward or outward depending on their orbital phase at the time of the flyby. Moreover, the scattered disk, which is essentially a transition zone between the classical Kuiper belt and the Oort cloud, is even more likely to respond. Many of these scattered disk objects are already in marginally stable orbits, kept in place largely by the long-range gravitational interactions with Neptune. A stellar flyby could easily unbind them, converting them into new long-period comets, or injecting them into sun-grazing orbits that take them deep into the inner solar system. There's also the question of the hypothetical Planet 9, a massive, unseen planet that some astronomers believe lurks in the distant outer solar system, somewhere between 400 and 800 Australian dollars. The theory arose from the unusual clustering of certain trans-Neptunian objects, TNOs, which appear to be shepherded into similar orbits by a common gravitational influence. If Planet 9 exists, Gliese 710's flyby, depending on its exact distance and vector, could potentially nudge its orbit or alter the orbits of the TNOs it governs. This could either enhance or disrupt the very clustering that first hinted at Planet 9's existence. But beyond the mechanics, there's a deeper cosmic truth: the Kuiper belt, and the outer solar system in general, is not isolated. It is part of the galactic ecosystem, subject to the comings and goings of nearby stars, the oscillations of the Sun through the galactic disk, and the tidal pull of the Milky Way itself. Gliese 710 is simply one of the better understood examples of this interaction. Over the course of billions of years, many such flybys have likely shaped the architecture of the Kuiper belt, stripping it of material, injecting new comets, or perhaps even introducing interstellar debris that now masquerades as native solar system material. And while a passage at 13,000 Australian dollars is unlikely to directly knock any large object from the Kuiper belt into Earth's path, it could subtly reshape the distribution of minor bodies in ways that become noticeable over thousands to tens of thousands of years. The orbits of objects like Sedna, Eris, and 2012 VP-113, all of which reside in the solar system's deep freeze, could gradually shift. Some might be pulled outward, others inward. Over millennia, these tiny changes accumulate, leading to a slow-motion rearrangement of the outer solar system. What's more, any comets nudged from the Kuiper belt or scattered disk into the inner solar system would arrive on relatively short timeframes compared to their Oort cloud cousins. While Oort cloud comets can take millions of years to reach the Sun, Kuiper belt comets can complete the journey in centuries or less. In theory, the initial wave of cometary activity sparked by Gliese 710 could be dominated by Oort cloud debris, but the secondary wave, possibly thousands of years later, might include perturbed Kuiper belt objects cascading inward in a delayed reaction. And then there's the observational angle. Astronomers today are already watching the Kuiper belt with ever-increasing interest. If Gliese 710's flyby produces changes in the orbits of known TNOs, or causes unexpected cometary outbursts centuries from now, it might be the first real-time glimpse of a solar system reacting to stellar intrusion. Future generations of scientists might even be able to watch the ripple effects unfold across centuries, mapping the transformation of orbits, densities, and impact rates in a kind of slow celestial ballet. In sum, while Gliese 710 is not expected to plunge directly into the Kuiper belt, its gravitational echo may nonetheless be felt. The frozen outlands of our solar system are not as silent as they seem. They remember past encounters, and they will record this one too, etched not in stone, but in orbits, tilts, and icy paths gently warped by a visitor from afar. Predicting the future of the solar system after a stellar flyby like Gliese 710's isn't something we can do on the back of an envelope. It requires supercomputers, statistical modeling, and deep astrophysical insight. Fortunately, astronomers have been running precisely these kinds of simulations for decades, trying to understand not only what happens when a star enters the Sun's neighborhood, but also what consequences ripple through the solar system for thousands, or even millions of years afterward. These are the simulations of chaos, and they reveal just how fragile and dynamic our cosmic environment truly is. The term chaos, in this context, doesn't imply randomness. It refers to deterministic chaos, where small changes in initial conditions lead to vastly different outcomes. The outer solar system, especially the Oort cloud and the scattered disk, is a perfect environment for this kind of behavior. Orbits are long, distances are vast, and the gravitational bindings are loose. Even a tiny gravitational nudge, barely noticeable at first, can compound over time until it alters the trajectory of a comet or icy body in dramatic fashion. Simulations of Glee 710's approach are essentially deep dives into that chaos, seeking patterns and predictions within a sea of possibilities. Most of these simulations begin with a realistic model of the Oort cloud, typically containing millions of massless test particles, each one representing a potential comet. These particles are distributed across a range of orbits, inclinations, and semi-major axes to mirror what we know, or suspect, about the real Oort cloud. Then, a virtual Glee 710 is introduced, based on Gaia's measurements. Its mass, velocity, approach angle, and closest distance to the Sun are all entered as parameters. When the simulation begins, gravity takes over. The star sweeps past the outer edge of the system, perhaps at 13,000 Australian dollars, perhaps closer or farther depending on the run, and the model tracks what happens next. Some comets are pulled inward, their long circular orbits disrupted into highly elliptical plunges toward the Sun. Others are flung out entirely, ejected from the solar system, their journeys redirected into the interstellar void. Still others are pushed slightly off balance, setting them on slow, uncertain paths that could take millennia to reach the inner planets, or never arrive at all. Across thousands of these simulation runs, consistent patterns begin to emerge. One of the most important findings is the timing and intensity of comet showers following such flybys. Simulations suggest that, for a flyby like Glee 710's, the first wave of comets dislodged from the Oort cloud wouldn't arrive immediately. There is a lag time, often tens of thousands of years, between the flyby event and the onset of a significant increase in comet activity in the inner solar system. This delay happens because the dislodged comets, even when nudged sunward, must travel vast distances on their new elliptical orbits. A comet starting from 20,000 Australian dollars, even at a modest velocity, can take hundreds of thousands of years to complete the inward plunge. But once that wave begins, it can persist for tens or even hundreds of thousands of years, resulting in a prolonged increase in impact risk for Earth and other inner planets. One well-known study led by researchers at the Max Planck Institute for Astronomy, using Gaia DR2 data, showed that Glee 710's flyby is expected to increase the flux of long-period comets by up to tenfold for a duration of a few million years. This represents one of the most significant cometary disturbances predicted from any known stellar flyby in the near future. These are not just theoretical risks, they are backed by robust, physics-based modeling. Other simulations have tried to correlate past mass extinctions with similar events. One idea, long debated, is that regular spikes in comet impacts, potentially tied to periodic stellar encounters, might explain extinction patterns observed in the geological record. Though Glee 710 isn't predicted to be responsible for any past event, simulations have helped support the idea that flybys like it could periodically reshuffle the deck of the solar system's icy reserves, triggering comet showers that ripple through deep time. Some simulations go even further. Advanced models now account for multi-body interactions, not just the Sun and the incoming star, but the complex gravitational interplay between the planets, the galactic tide, and even hypothetical objects like Planet 9. These high-resolution simulations, often run on GPU-based supercomputers, can process billions of calculations per second, allowing researchers to test extremely fine-grained variables. They can model not only when and how many comets might be perturbed, but which specific regions of the Oort cloud are most vulnerable depending on the angle and speed of the flyby. Interestingly, not all simulations show catastrophe. In many runs, Gliese 710's approach results in a mild reorganization of outer solar system bodies. Some comets are lost, some are gained, and a few might fall sunward, but the solar system remains stable. In others, especially those where Gliese 710 passes closer than 10,000 Australian dollars or carries an unseen companion, the results become more dramatic. One simulation, which explored a worst-case approach distance of under 5,000 Australian dollars, resulted in over 100,000 comets being nudged into sun-crossing orbits over a period of 2 million years. These simulations also help prepare us. By modeling the precise gravitational mechanics of flybys, we gain insight into what warning signs to watch for, how to detect a slow trickle of comets years before a true storm arrives. We also learn more about which regions of the sky to monitor for inbound threats. If Gliese 710 does trigger a wave of long-period comets, they will likely arrive from a specific region aligned with the star's incoming trajectory, forming a comet shower cone in space. Future telescopes, like the Vera C. Rubin Observatory, may one day catch the early messengers of such a storm. Perhaps most fascinating is how simulations are increasingly being paired with machine learning and artificial intelligence. Neural networks trained on millions of simulated encounters can now predict cometary impact probabilities far faster than traditional models, allowing for a real-time adaptive approach to long-term planetary defense. Though we're still in the early days of such hybrid techniques, they may be crucial tools for future generations tasked with tracking and mitigating the consequences of ancient stellar flybys. In the end, the value of these simulations lies not just in predicting impacts, but in understanding the living memory of the solar system. Every orbit, every distant object, every icy body wandering in the dark bears the fingerprint of a long-past encounter. Gliese 710 will leave such a fingerprint, too. And thanks to our simulations of chaos, we will know where to look for it, what to expect, and how to read the signs in the sky. It's easy, almost instinctual, to dismiss a threat projected to occur 1.29 million years from now. After all, what's a million years to a creature that lives less than a century? But when we shift our perspective, stretch it beyond the narrow confines of human history and into the vast scale of cosmic time, that number begins to change shape. In the language of stars and galaxies, 1.29 million years is not distant. It is immediate. It is imminent. And for a solar system that's been orbiting the galaxy for over 4.5 billion years, a million years is a mere blink. To put it in perspective, the last time Earth was visited by a significant stellar flyby that came close enough to meaningfully disturb the Oort Cloud may have been around 70,000 years ago, when Scholz's star passed by at a distance of roughly 52,000 Australian dollars. That's well beyond Gliese 710's projected approach. And even that encounter, relatively far by Oort Cloud standards, may have nudged a few icy bodies into new orbits, though none have yet reached the inner solar system. What makes Gliese 710's passage so noteworthy is not just its proximity, but how soon it's coming, on the scale of the solar system's rhythm. Consider this: Earth formed 4.5 billion years ago. Dinosaurs roamed the planet around 230 million years ago, and went extinct about 66 million years ago. Our own species, Homo sapiens, has only existed for around 300,000 years. The entire span of human civilization, from the earliest cities to space exploration, fits neatly into just the last 10,000 years. Compared to that, 1.29 million years is undeniably vast. But not to the solar system. Not to the galaxy. And perhaps not to the legacy of life that may still exist when Gliese 710 arrives. In terms of galactic motion, the Sun completes one orbit around the Milky Way roughly every 225 to 250 million years. So in 1.29 million years, the solar system will have traveled just about 0.5% of the way along its galactic path. That's almost nothing. A small turn. A fraction of a curve around the galaxy's spiral arm. And yet, in that sliver of motion, an alien sun will pass by, silent, cold, and possibly disruptive. The timescale of risk also intersects with another sobering reality: Earth's biosphere is not eternal. Mass extinctions have occurred before, at least 5 major ones, each reshaping the landscape of life. Some were driven by volcanic activity, others by asteroid impacts, and some, potentially, by surges in cometary bombardment, possibly triggered by distant stellar visitors. If Gliese 710's gravitational ripple sends a wave of comets toward the inner solar system, we could be looking at a 6th extinction event sometime after its closest approach. Not immediately, but potentially within the next few million years, as perturbed comets reach the inner solar system on elongated, deadly trajectories. The Earth has endured cosmic disasters before. The Chicxulub impact that wiped out the dinosaurs was caused by a 10-kilometer object, possibly a comet or asteroid. That single impact led to a 70% extinction rate, plunged the planet into darkness, and rewrote the course of evolution. The odds of a single dislodged comet from Gliese 710's influence doing the same are low, but the cumulative risk over millions of years of heightened cometary activity is far from negligible. This is why the timescale matters, not because we expect catastrophe tomorrow, but because cosmic timelines operate on slow escalations. Gliese 710 will pass, and the results of that passage will unfold slowly, like ripples spreading across a vast lake. Some comets dislodged from the Oort Cloud may take millions of years to reach perihelion. Others, especially those in the inner edge of the cloud, may arrive in just tens of thousands of years. It's a staggered threat, less a wave, and more a storm system that lasts for epochs. It also challenges us to think long-term, far beyond the lifespan of individuals or even civilizations. While it's unlikely that we, as the humans of today, will be around to witness Gliese 710's flyby, the descendants of our species might, if they survive, evolve, and maintain a foothold in the cosmos. For them, understanding Gliese 710's passage may not be academic curiosity. It may be mission-critical knowledge: how to deflect comets, how to monitor distant perturbations, how to read the sky for threats born in an ancient star's wake. And yet, despite its proximity on the cosmic clock, Gliese 710 also serves as a test of foresight. It reminds us that astronomy isn't just about observing the heavens for beauty, it's also about planning for survival. We study these distant stars, track their trajectories, and simulate their effects because knowledge, especially in matters of cosmic dynamics, is a form of early warning. Not for the next decade, not for the next century, but for the next age. This kind of long-term thinking is rare in human history. Most societies are built around short cycles, harvest seasons, generational shifts. But the universe doesn't care about our clocks. Comets don't ask for permission to approach. They fall when disturbed, and they disturb when they fall. Gliese 710's future flyby demands a cosmic awareness, an ability to perceive risk and consequence on geological and astronomical timescales. Not to panic, but to prepare. To begin a lineage of observation that spans not years, but millennia. A million years may seem far away today, but for those who will one day live in its shadow, the work of astronomers now, using Gaia, using simulations, using the cold arithmetic of gravitational dynamics, may be the first defense against an event they will inherit, and possibly endure. So no, 1.29 million years is not too far away to matter. In cosmic terms, it's just over the horizon. And by watching that horizon, we become something remarkable, a species aware not only of its present, but of its deep future. If Gliese 710 seems like a rare cosmic anomaly, a rogue interloper with terrible timing, then the statistics may come as a surprise. Because stellar flybys like this aren't just real. They're common. Not in human terms, perhaps, not in the scale of decades or even millennia, but on the stage of galactic evolution, stars are constantly passing each other, weaving through the galaxy like dancers in a slow, gravity-bound ballet. The question isn't whether stars pass close to the sun. The question is, how often does it happen? And more crucially, how close do they get? The sun is not drifting through the galaxy alone. It's orbiting the Milky Way's center along with hundreds of billions of other stars, each following its own trajectory through the complex gravitational contours of the galactic disk. These stars, including red dwarfs, yellow dwarfs like our Sun, massive blue giants, and the occasional white dwarf or brown dwarf, all move in slightly different directions, with slightly different speeds. Over time, their paths cross, and occasionally, they pass near each other. Astronomers estimate that the Sun experiences a close stellar flyby, within 1 light-year, about 63,000 Australian dollars, approximately every 100,000 to 200,000 years. That might sound frequent, but most of these pass-bys happen well outside the range of the Oort Cloud, and their gravitational influence is typically negligible. But if we refine our definition and look for truly close encounters, say within 20,000 Australian dollars, deep enough to seriously disturb the Oort Cloud, then the rate drops. Current simulations suggest such events occur roughly once every 1 to 2 million years. That means Gliese 710, expected to pass within 10,000 to 20,000 Australian dollars, fits right in line with this statistical rhythm. It's not a once-in-a-billion years catastrophe. It's part of the normal operating conditions of the solar system. It's the price of existing in a galaxy teeming with motion. To put this into context, we can examine the solar neighborhood, the region within about 20 light-years of the Sun. There are over 300 stars and stellar systems in that relatively small volume, and they are not stationary. Each one moves relative to the Sun, some fast, some slow, and their positions shift gradually over time due to what astronomers call stellar proper motion. As we collect more precise data from missions like Gaia, we're able to project their past and future trajectories, identifying not just Gliese 710, but dozens of potential flybys, past and future. For example, shows a star passed within 52,000 Australian dollars of the Sun just 70,000 years ago. While it didn't enter the inner Oort cloud, it came closer than most stars and may have stirred up some outer Oort objects. Interestingly, Scholz's star is a binary system, a red dwarf and a brown dwarf companion, making it particularly massive relative to most flyby stars. Its flyby was quiet, but not irrelevant. Looking forward, other stars are on approach too. For instance, HIP 85605 was once believed to be on a dangerously close trajectory, possibly passing within 0.1 light-years in the next 500,000 years. However, more accurate data from Gaia has since revised its path and distance significantly, making it a far less concerning object than Gliese 710. This shows just how important precision is in these measurements. One new data release can mean the difference between harmless and potentially disruptive. When we look at the galaxy more broadly, we find that stellar flybys have likely played a critical role in shaping not just our solar system, but planetary systems across the Milky Way. A close stellar encounter during the early formation of the solar system may have helped sculpt the edges of the Kyper belt. In young star-forming regions like the Orion Nebula, stars are densely packed, and close passes are far more frequent, possibly even reshaping the formation of planets by pulling disks apart or capturing rogue objects. In fact, there is a growing belief among astrophysicists that the orbits of some of the most distant objects in our solar system, such as Sedna and 2012 VP113, may have been shaped by an ancient stellar encounter. These objects follow highly elliptical orbits that are difficult to explain through interactions with the known planets alone. A well-timed stellar flyby several billion years ago could have injected just enough gravitational torque to throw them onto their current paths, silent evidence of a long-forgotten visitor. And that's the fascinating twist. Most stellar flybys don't leave an obvious scar. They don't crash into anything. They don't tear planets from their stars. Instead, they leave subtle fingerprints, orbital anomalies, scattered debris, tilted disks. And unless we look carefully, unless we run simulations backward through time or detect the long-period comets they unleash, we might never even know a star passed by. That's why Gliese 710 is such an important case study. It is not the first, and it won't be the last, but it's the one we see coming, in detail, with precision, long before it arrives. It gives us a chance to observe not just the moment of passage, but the before and after, the transformation of the Oort cloud, the increased flux of comets, the possible impacts on Earth and other planets. It allows us to study the mechanics of a stellar flyby not as an abstract event in a computer model, but as a real phenomenon with measurable outcomes. As data continues to pour in from Gaia and future missions, astronomers expect to refine the list of past and future flybys. We may find that Gliese 710 is only the most visible tip of a much larger iceberg, one of many stars threading their way through the solar system's distant periphery, each one with the potential to reshape its icy outskirts in subtle or spectacular ways. So how often do stars pass this close? Often enough to shape the solar system's structure. Rarely enough that each one leaves a unique imprint. And in the case of Gliese 710, just close and soon enough to warrant our full attention. While Gliese 710 captures headlines for its projected close encounter with our solar system, it is far from alone. The Sun has never traveled through the galaxy in isolation. Over the course of billions of years, it has crossed paths with many stars, some that passed quietly, others that likely stirred the solar system's icy outskirts, and a few whose presence we're only now beginning to understand. Studying these other stellar visitors helps us place Gliese 710 in proper context, revealing that the story of flybys is not a rare one-off event, but part of the dynamic and ongoing interstellar choreography that defines our corner of the galaxy. One of the most well-known stellar flybys in recent astronomical memory is Scholz's star, a binary system consisting of a low-mass red dwarf and an even dimmer brown dwarf. Around 70,000 years ago, this system passed within about 52,000 Australian dollars of the Sun, roughly 0.25 light-years away. That's far beyond the planetary zone, but still well within the estimated bounds of the Oort Cloud. This encounter, though distant in space, is extremely close in time. It occurred during the age of anatomically modern humans. In fact, our ancestors were already using tools and forming early cultures when Scholz's star swept by in the sky, though, due to its faintness, it likely would have been invisible to the naked eye, even at closest approach. The evidence for Scholz's star's flyby was only uncovered in the last decade, using a combination of proper motion analysis and radial velocity measurements. Its relatively low velocity compared to the Sun, around 83 km per second, much slower than average for stars passing through the solar neighborhood, allowed it to linger longer in our vicinity than many other stars do. Some models suggest that it may have caused minor disturbances in the outer Oort cloud, though no specific comet influx has been linked to it yet. Beyond Scholz's star, several other stellar systems are known to be approaching, or have already passed near, the Sun. Some of them are worth noting for their proximity, others for their potential to disturb the Oort cloud, and still others because of the uncertainties that make them intriguing. One such example is Gliese 445, a red dwarf star located about 17 light-years away in the constellation Commonality. It is currently moving toward the Sun and is projected to come within 3.45 light-years in about 40,000 years. That's not close enough to disturb the Oort cloud in a significant way, but it does demonstrate how frequently nearby stars drift in and out of our galactic neighborhood. Gliese 445 will never pose a threat, but it may one day be one of the brightest stars in our night sky. Then there was GJ 710, the original name for Gliese 710 under a different catalog, which underwent heavy scrutiny after Gaia's second data release. It remains, to date, the most significant future flyby identified with high precision. However, before Gaia refined its data, astronomers once believed that HIP 85605 might pose an even greater threat. HIP 85605, a K-type orange dwarf star, was once estimated to pass within 0.1 light-years of the Sun, less than 5,000 Australian dollars, in just 300,000 years. Such a flyby would have brought it into the very heart of the Oort cloud, with possible consequences for both the outer and inner solar system. But later Gaia data revealed that HIP 85605's position and motion had been mischaracterized, and its projected trajectory was dramatically revised. It now appears that HIP 85605 will miss the Sun by a much wider margin, possibly several light-years. It's a textbook example of how improved measurements can turn an apparent threat into a non-event. Another candidate of interest is WISE 0855-0714. One of the coldest brown dwarfs ever discovered. Located just 7.2 light-years away, this object is incredibly faint, only detectable in infrared, and barely emits visible light. Its motion across the sky is still being refined, but due to its proximity, astronomers have been studying its trajectory carefully. While it's not on a direct approach to the Sun, its existence serves as a reminder that numerous faint objects, especially brown dwarfs and low-mass red dwarfs, may be moving nearby undetected. The discovery of WISE 0855-0714 has prompted speculation that other, similar dark objects could eventually make a close pass without us noticing until relatively late in their approach. In fact, one of the lingering fears in planetary defense circles is the possibility of a rogue object, a brown dwarf, a rogue planet, or even a black hole, approaching the solar system on an uncharted course. These objects emit little or no light, making them hard to spot with traditional telescopes. They could remain hidden in the cosmic background until suddenly revealed by their gravitational influence on outer solar system bodies, or by an unexpected glow from heated dust as they enter the heliosphere. There's also speculation, still theoretical but intriguing, about the long-past influence of stellar flybys during the early history of the solar system. Some models suggest that during the solar system's formation within a stellar nursery, a nearby passing star could have stripped the Sun's protoplanetary disk, truncated its outer edge, or even contributed material, some of which might now reside in the Kyper belt or Oort Cloud. If true, it means that stellar flybys may have helped define the boundaries of our solar system from its very beginning. When we consider all of these stars, past, present, and future, we begin to realize that Glee's 710 story is not isolated. It is part of a wider galactic dance, in which stars pass each other like ships in the night, unaware of the tiny planets and icy debris fields that might lie just beyond their reach. While most of these stars will pass at safe distances, some come close enough to leave a mark. Glee's 710 is one of them. Scholz's star was another. Others still await discovery, quiet stars drifting through the void, each one a potential architect of subtle orbital chaos. This cosmic traffic reminds us that our solar system is not protected by walls or boundaries. It is open, vulnerable, and always moving through a crowded and evolving galaxy. Studying these other stars on approach, tracking their paths, refining their speeds, estimating their influence, isn't just an academic exercise. It's part of our ongoing effort to understand the full complexity of the Sun's celestial neighborhood, and the hidden risks that drift silently in the dark. When imagining the trajectory of Glee's 710, one might wonder, however improbable, what would happen if, instead of passing by, it somehow became gravitationally ensnared by our solar system. Could a visiting star, however faint and slow, be captured and become a new member of our celestial family? Could Glee's 710 end up orbiting the Sun, not just brushing past it in the galactic night? While the answer is almost certainly no, it opens the door to a fascinating line of speculation, grounded in physics yet steeped in the improbable. The idea that a star could be temporarily or even permanently captured by the Sun's gravity. It's the kind of scenario that challenges our understanding of orbital dynamics, celestial mechanics, and the delicate balancing act that governs motion in space. To begin with, for any object to be captured by another, it must lose enough kinetic energy to drop below the escape velocity of the system it is passing. In the case of Glee's 710, it is currently cruising through the galaxy at about 50,000 km per hour relative to the Sun. That's incredibly fast, more than enough to escape the Sun's gravity after it reaches periapsis, even at its predicted closest approach of around 10,000 to 20,000 AU. For a true capture to occur, Glee's 710 would need to shed a massive portion of its energy. That typically requires some form of gravitational braking, such as a three-body interaction, something like the classic physics problem where a spacecraft performs a gravity assist around a planet to change speed. In the case of stars, the only natural way for this to happen is through a highly improbable multi-body encounter. For instance, Glee's 710 flying close enough to a large object in the outer solar system, say, a massive undiscovered planet or a dense comet swarm, and transferring energy in such a way that it becomes gravitationally bound to the Sun. But even that is vanishingly unlikely. The mass of Glee's 710 is about 60% that of our Sun, too heavy to be easily redirected by any planetary object in the solar system. Jupiter, for all its might, is still only about 0.1% the mass of the Sun and lacks the gravitational authority to significantly change the momentum of a passing star. Even a theoretical Planet 9, if it exists and has 5 to 10 Earth masses, would be a lightweight against such a stellar interloper. Glee's 710 sheer momentum and speed ensure that it will pass through unbound, like a comet through a planetary system, barely noticing the gravitational presence of our planets and dwarf planets. Yet, some theorists have explored scenarios of temporary capture, not permanent binding. This occurs when an object's trajectory is warped just enough for it to loop around its host star one or more times before escaping again. In the case of Glee's 710, such a capture would require it to pass extremely close to a dense cluster of mass in the solar system's outskirts, perhaps a concentration of unseen dark matter, a hypothetical concept, or even a previously unknown substellar object. The likelihood is still exceedingly low, but in computer simulations involving massive flybys, temporary orbits can occur under very specific conditions. Even more exotic is the idea of binary capture. Imagine Glee's 710 approaching the solar system not alone, but with a hidden companion, a brown dwarf, or even a gas giant in a wide orbit. If the Sun's gravity were to interact strongly with this companion, tidal forces could tear it away, binding the lower mass object to the Sun while Glee's 710 escapes alone. This type of exchange has been seen in galaxy-scale simulations and in star cluster dynamics, where lower mass members of a binary system are captured while their heavier partners continue on their paths. But again, this is mostly theoretical, and no such companion has been observed with Glee's 710, though our instruments might not be sensitive enough to detect a cold, dim brown dwarf at its current distance. Another intriguing possibility is not gravitational capture, but optical or observational capture, in the sense that Glee's 710's passage might lead to the Sun stealing material from its outskirts. For instance, if Glee's 710 harbors a large, extended cloud of comets or icy bodies, analogous to our own Oort Cloud, then some of that material could be gravitationally perturbed during the flyby and become part of the solar system. We would, in essence, collect flotsam from another star system. These objects, once caught, might settle into distant orbits around the Sun, becoming new residents of our already chaotic outer shell. There's even speculation, still in the realm of science fiction for now, that an advanced civilization could engineer such a capture. A Type 2 civilization, according to the Kardashev scale, might hypothetically possess the technological means to redirect stellar bodies, either for energy harvesting, terraforming, or stellar engineering. In that context, capturing a low-mass star like Glee's 710 could offer immense advantages. It could be used to prolong the lifespan of a fading system, act as a secondary energy source, or even serve as a cosmic tug to migrate the solar system itself. Though this lies far outside our capabilities, it reminds us how profoundly the rules of astrophysics shift when intelligence and intent enter the equation. Still, in realistic terms, bound by natural gravitational dynamics and known celestial mechanics, the chance of Glee's 710 becoming a gravitational satellite of the Sun is near zero. The numbers simply don't allow it. Its velocity, mass, and trajectory are all wrong for capture. It will pass by, leaving ripples in the Oort Cloud, perhaps stirring a few comets loose, and then continue on its slow journey through the galaxy, fading into the background once again. And yet, even knowing that, the thought persists, what if? In the grand cosmic lottery, where time stretches into the billions of years, and stars drift through the spiral arms like luminous ships, there will inevitably be flybys more complex than Glee's 710s. Ones with multiple companions, unusual angles, or perfect gravitational conditions. Someday, perhaps, a star might be captured. And if that ever happens, the solar system will never be the same again. The idea of intervention, of doing something about Glee's 710 or its cascading consequences, veers sharply away from passive astronomy and into the thrilling, uncertain territory of cosmic engineering. While current humanity is bound by the limitations of chemical rockets and observational telescopes, it is within the realm of speculative science to imagine a future where we are no longer just observers of the cosmos, but active participants in shaping its events. The question is simple. Could we do something to prevent or mitigate the effects of Gliese 710's passage, or its cometary aftermath? To consider this, we must first break the question into two parts. Could we alter Gliese 710's path? And could we protect ourselves from the resulting cometary threat? Each presents unique, colossal challenges. Let's begin with the more extreme proposition, altering the path of a star. Gliese 710 is a star with about 0.6 times the mass of the Sun, moving at roughly 50,000 kilometers per hour, and passing at a minimum of 10,000 Australian dollars from our system. Altering its trajectory even slightly would require astronomical energy, far beyond the reach of any current or near-future technology. To exert any meaningful gravitational influence over such a mass would take not just thousands or millions of tons of propellant, but entire planetary-scale projects. In purely speculative terms, an ultra-advanced civilization, perhaps a Type 2 or Type 3 on the Kardashev scale, might have access to the energy required to accelerate or decelerate stars, using megastructures like stellar engines or Shkadov thrusters. A Shkadov thruster is a hypothetical concept where a massive, mirrored megastructure is built partially around a star to reflect its light in one direction, creating an uneven radiation pressure that slowly propels the star in the opposite direction. Even then, the movement induced is glacial, measured in millimeters per second, and only noticeable over hundreds of thousands of years. But here's the twist: if we could build such a megastructure around a star, or use some other method like gravitational tugs, it wouldn't be Gliese 710 we'd move. It would be the Sun. Yes. If a civilization advanced enough to manipulate stellar motion existed, it might prefer to move its own star and planetary system rather than deflect a passing one. This is the logic behind the Kaplan thruster, a proposed concept that would use fusion-powered propulsion and stellar wind control to slowly push the Sun itself through space, dragging the solar system with it to avoid long-term cosmic threats. Of course, such notions exist entirely in the theoretical. For us today, or even in the foreseeable future, Gliese 710's trajectory is immutable. It is a force of nature we can only observe and model, not redirect. But the second part of the equation, mitigating the potential flood of comets dislodged by Gliese 710's gravitational ripple, is far more plausible, even for a moderately advanced civilization. If a comet storm does occur, it won't arrive suddenly. Based on simulations, the first major wave could take tens of thousands to hundreds of thousands of years to reach the inner solar system. That's time, precious time, to prepare. One option is planetary defense systems, the kind that are already under development today. NASA's DART mission, Double Asteroid Redirection Test, proved that kinetic impactors could nudge the orbit of a near-Earth object. Scaling this up to a large long-period comet would require much more force, but the principle is the same: detect, track, and deflect. For icy bodies that are loosely held together, another possibility is solar ablation. By directing concentrated sunlight or powerful lasers at a comet, we could vaporize part of its surface, generating thrust that slowly alters its trajectory. This would need to occur far from Earth, perhaps hundreds of millions of kilometers out, but it is well within the realm of physical possibility. Even more futuristic is the idea of asteroid shepherding fleets, constellations of autonomous spacecraft, each equipped with ion drives or nuclear propulsion systems, capable of attaching themselves to incoming objects and guiding them to safer orbits. In theory, they could act as cosmic air traffic controllers for decades or centuries, managing a trickle of comets as they fall inward from the distant reaches of the Oort Cloud. And what if that trickle becomes a deluge? If a full-scale comet storm ever occurred, something comparable to the hypothesized event that triggered the late heavy bombardment, then space-based shielding might be considered. Massive arrays of deflector systems placed at Earth's L1 Lagrange point could serve to vaporize or fragment incoming bodies. Some designs propose magnetic deflection systems, while others involve clouds of dust or debris launched into space to act as kinetic absorbers. Still more speculative is the idea of terraforming Earth itself to withstand impacts. Subterranean cities, energy domes, or planetary-scale impact mitigation systems might one day allow humanity, or its descendants, to ride out a centuries-long period of increased bombardment. It's a grim thought, but one that takes into account the resilience of life in the face of deep time and astronomical odds. Then there's the possibility that we might simply leave. Long before Glee 710's flyby reaches its full consequence, an interstellar-capable civilization might already have seeded colonies beyond the solar system. Whether on nearby exoplanets or aboard generational ships, they might observe the results of the comet storm from a safe distance, watching their home system undergo a celestial trial they have long outgrown. And yet, even with all of these hypotheticals, the heart of the question remains, should we do anything? If we have tens or hundreds of thousands of years to prepare, and the risk is probabilistic, not guaranteed, do we act? Or do we observe, catalog, and wait? Ultimately, Glee 710 invites us not just to understand stellar motion and cometary dynamics, but to contemplate our place in the universe as agents of foresight. We are the first species, as far as we know, to not only track a star across millions of years of future time, but to ask, what should we do about it? Perhaps, in the distant future, when descendants of Earth look back on Glee 710's slow glide across the galactic sky, it won't just be a case study in orbital mechanics. It will be remembered as the first moment humanity considered intervening in the stars themselves, not with fear, but with vision. Long before telescopes, before astronomy, before language, long before even mammals ruled the Earth, our planet bore the scars of cosmic violence. These scars are written in stone, embedded deep in the crust, and locked inside layers of sediment and fossils. Earth's history is not a calm and steady march of life. It is a story of sudden, catastrophic change, some of it caused not by what happened on Earth, but by what came hurtling in from beyond it. Among the most haunting possibilities in planetary science is that extinction events, those abrupt collapses in biodiversity that have reset the trajectory of evolution again and again, may have been triggered by cometary bombardments, some of which could have been the indirect result of stellar flybys like the one Glee 710 will soon perform. The most famous extinction event in Earth's history, the one that ended the reign of the dinosaurs around 66 million years ago, is linked to a single massive impact. The Chicxulub crater, buried beneath the Yucatan Peninsula in Mexico, spans over 150 kilometers. It was caused by a 10 to 15 kilometer wide object slamming into Earth with an energy equivalent to billions of Hiroshima-sized atomic bombs. The impact ejected dust and vapor into the atmosphere, blocked sunlight, disrupted global climate, and caused a cascading ecological collapse. 75% of all species vanished, including the non-avian dinosaurs. While the impactor is often described as an asteroid, some scientists believe it could have been a long-period comet, one flung from the Oort Cloud, possibly destabilized by a prior stellar encounter. In 2021, a provocative paper by Harvard astronomers proposed that the Chicxulub impactor may have originated from the outer solar system, perturbed by Jupiter's gravitational influence after being nudged inward. Though controversial, this theory reignited the question: are comets more responsible for mass extinctions than we thought? If Glee 710, as predicted, disturbs the Oort Cloud and unleashes a rain of comets toward the inner solar system, it may replicate, on a much smaller scale, conditions like those that led to Chicxulub. But that wasn't the only time in Earth's history that a mass extinction coincided with possible extraterrestrial involvement. Take, for instance, the late Devonian extinction, roughly 370 million years ago. This prolonged period of biodiversity loss wiped out about 75% of species, particularly marine life. The causes remain debated, but evidence has been found of impact craters dating to around this time. One example is the Siljan crater in Sweden, a roughly 50-kilometer wide structure that may have played a role. While not definitive proof of a comet strike, the timing is suggestive. Then there's the end Permian extinction, or the Great Dying, which occurred 252 million years ago. It remains the most devastating mass extinction event known, eliminating over 90% of marine species and 70% of terrestrial vertebrates. While this event is primarily attributed to massive volcanic activity, specifically the Siberian traps, some researchers speculate that an extraterrestrial trigger, possibly an impact, may have worsened or initiated the event. Supporting evidence includes the discovery of rare minerals like fullerenes containing extraterrestrial gases, though this remains a topic of intense debate. Similarly, the end-Triassic extinction, about 201 million years ago, and the end-Cretaceous event that followed were both abrupt and transformative, clearing the evolutionary slate for new lifeforms to flourish. While many mass extinctions can be linked to internal planetary upheavals, volcanoes, shifting climates, changing ocean chemistry, the possibility remains that comet showers, triggered by stellar flybys, have served as cosmic catalysts, igniting these planetary resets. What links these theories together is the role of the Oort Cloud, that vast, distant halo of icy objects that lies tens of thousands of AU from the Sun. Normally stable, the Oort Cloud exists in delicate gravitational balance. But when a star like Gliese 710 sweeps through the cloud's outskirts, that balance is upset. Thousands, possibly millions, of comets could be dislodged. Most will drift harmlessly into interstellar space, but a fraction will fall inward, pulled by the Sun's gravity into long, sweeping orbits that carry them through the planetary zone. Some of these comets may break apart in the inner solar system. Some may burn up in the Sun. Some may miss everything. But others, just a few, could find themselves on collision courses with Earth, Mars, Venus, or the Moon. Given their long, dark trajectories, these comets are among the most difficult objects to detect in advance. They often appear with only months of warning, if that. And due to their size and speed, even a single impact could spell global catastrophe. That is why the connection between past extinctions and cometary bombardments is more than academic curiosity. It's a warning, a precedent. Earth has endured cosmic calamities before, and if Gliese 710's passage mirrors those ancient gravitational nudges, we may witness another storm, long after its quiet crossing of the solar periphery. There's also an eerie pattern in the fossil record that may support this idea. Some studies suggest that mass extinctions follow a rough periodicity, occurring every 26 to 30 million years. This has led to speculative models involving a hypothetical nemesis star, a dim companion to the Sun that periodically disturbs the Oort Cloud. Though no such star has been found, the notion remains fascinating, especially in light of objects like Gliese 710, which could mimic such a periodic intruder. Could multiple past extinctions have been triggered by similar flybys? Could life's long evolutionary arc be punctuated by cosmic tides of destruction and renewal? Gliese 710 won't bring fire and fury itself. It will pass quietly, a dim, orange point in the sky. But what it stirs in its wake, that's the true threat. If it shakes loose even a handful of icy deathbringers from the Oort Cloud, it could initiate a chain of events not unlike those that ended the reign of dinosaurs or reshaped the oceans of the Devonian world. In understanding ancient impacts and extinctions, we find not just stories of death, but the blueprint for vigilance. Earth has been struck before. It will be struck again. But next time, we may not be blind to the danger. Next time, perhaps, we will see the signs in advance, starting with a single star, moving silently toward us from the constellation Serpens. Though Gliese 710 stirs unease with its trajectory through our galactic neighborhood, it also offers an unprecedented scientific opportunity, a moment in deep time where a star's flyby, observable both in advance and in its aftermath, could illuminate some of the darkest corners of astrophysics and planetary science. Rather than being just a threat to catalog, Gliese 710 might become one of the most informative events we've ever had the chance to study. It presents a natural experiment on a cosmic scale, one that could reshape our understanding of how solar systems evolve, how planetary environments are perturbed, and how life-bearing worlds might emerge, or fall, in the wake of stellar encounters. In essence, Gliese 710 offers the opportunity to observe a solar system being nudged by a star in real time. Not in the fast-paced drama of cinematic collisions or blazing supernovae, but in the quiet gravitational pull that unfolds over tens of thousands of years. It's a slow-motion experiment that we can begin modeling and observing long before the star even arrives. Let's start with one of the most tantalizing scientific prospects, the reorganization of the Oort Cloud. Despite being hypothesized nearly a century ago, the Oort Cloud remains one of the most mysterious structures in our solar system. No spacecraft has ever ventured there. No telescope has directly imaged its icy bodies. Everything we know about it comes from the orbits of long-period comets and dynamical models. But when Gliese 710 makes its close approach, we'll be able to observe in real time how its gravity perturbs that fragile halo of icy debris. For the first time, scientists will have an identifiable perturbing agent, a known mass, speed, direction, and timing, and can then track the resulting trajectories of dislodged objects. The comets it triggers will carry the fingerprints of Gliese 710's influence. Their orbits, velocities, and time of appearance will help us reverse engineer the Oort Cloud structure, how dense it is, how its mass is distributed, and how its members respond to external forces. Gliese 710 could become the best gravitational probe we've ever had for exploring the invisible edge of the solar system. Beyond just mapping the Oort Cloud, the flyby gives us a live demonstration of how planetary systems can be disrupted by passing stars, a process believed to be common throughout the galaxy. Observations of exoplanetary systems have shown us immense diversity: hot Jupiters in tight orbits, eccentric gas giants, planets and misaligned planes. Many of these features are believed to arise from early gravitational chaos, possibly involving flybys in stellar nurseries or later in stellar lifetimes. Gliese 710 provides us with a scaled-down version of these interactions, a way to model, test, and simulate how much disruption is possible from an interstellar visitor. This isn't just theory. With advanced simulations, astronomers can model thousands of variations of Gliese 710's passage, adjusting for slight changes in its velocity, mass, and approach angle. These simulations can predict not just the rate of comet influx, but also the possibility of gravitational kicks to trans-Neptunian objects or alterations in the orbits of long-period comets already inbound. Each data point helps refine our understanding of orbital mechanics on cosmic timescales. The event also invites advancements in high-precision observation and prediction tools. Tracking the flyby with accuracy will require continued data from missions like Gaia, as well as next-generation observatories like the Vera C. Rubin Observatory and Nancy Grace Roman Space Telescope. These tools will detect faint Oort Cloud comets as they begin their long fall toward the Sun, letting us verify our models in real time. The sheer predictive power necessary to model millions of potential orbits and interactions will push the limits of computational astrophysics, driving innovation in both software and processing power. Another promising scientific avenue is the study of interstellar transfer of material. When two solar systems pass close to each other, there's a non-zero chance that small objects can be exchanged. Comets, asteroids, or even rogue planets might be stripped from one system and captured by another. Gliese 710 may have its own Oort Cloud analog, and its passage through our outskirts could result in a swap of icy bodies. If even a handful of such objects are later detected and confirmed to originate from a different stellar chemical signature, we would have physical samples of another star's debris without ever leaving our own system. This opens profound questions about the cosmic mixing of materials. If stellar flybys regularly seed one solar system with fragments of another, then the building blocks of life, or even dormant microbial life itself, could potentially be exchanged across star systems. It's a cornerstone of the panspermia hypothesis, and though speculative, Gliese 710 provides a rare chance to look for such interstellar transfers in action. Moreover, the psychological and philosophical implications are just as powerful. For the first time in history, a species, ours, can predict a stellar encounter with such detail and foresight that we can begin studying it a million years in advance. That level of predictive astronomy is something no other known species has achieved. In this way, Gliese 710 becomes a monument to human foresight and inquiry, a cosmic event that unites observers across millennia. Educational institutions, too, will benefit. Future generations will grow up with this event as a case study, following it from a line of code in a Gaia data release to a global research program spanning centuries. Gliese 710 will be a beacon in scientific curricula, taught alongside Newton's laws and Kepler's ellipses, showing students that the solar system is not a closed, static entity, but a fluid, interacting participant in a vast galactic ecosystem. Its flyby also challenges planetary scientists to refine their planetary defense strategies. Even if Gliese 710 doesn't cause a major impact event, the increase in long-period comet activity it might trigger serves as a full-scale planetary defense drill, albeit on a generational timeline. It forces us to ask, how can we track icy bodies arriving from the Oort Cloud? How can we model gravitational chaos over hundreds of thousands of years? How do we coordinate international efforts for a threat that is distant, diffuse, and uncertain? These questions aren't just theoretical. Already, Earth-based surveys are preparing to expand their reach into the outer solar system. Missions like LSST, Legacy Survey of Space and Time, are expected to detect thousands of long-period comets and minor planets, providing baseline data that will be critical when Gliese 710's influence begins to manifest. By comparing comet influx rates now to those observed over the coming millennia, we'll be able to directly measure the star's impact on our system. And the value isn't just scientific. It's cultural. Gliese 710 represents a narrative, the story of a silent star approaching not with violence, but with the promise of transformation. Its appearance could become a milestone event in the collective human timeline, much like the Halley's Comet passages of antiquity, or the 1994 Shoemaker-Levy 9 impacts on Jupiter. Astronomers of the far future may watch it brighten in the night sky, knowing its legacy spans from Earth's prehistoric past to its still-forming future. In the end, while Gliese 710 may not directly endanger our planet, its true power lies in what it teaches us. It will give us a once-in-a-million-year view into the slow collision of gravitational systems, the reshuffling of icy archives, the invisible tendrils of force that shape the fates of worlds. It is not a catastrophe, but an opportunity, perhaps the greatest long-term experiment nature has ever set before us. To study it is to study change itself. To track its path is to map the silent interplay of stars. And to prepare for it is to become stewards not just of Earth, but of our whole solar system. Despite the dramatic nature of Gliese 710's impending flyby, one of the most important scientific clarifications is also one of the least intuitive. It will not directly affect the Sun or the planets in any noticeable gravitational way. This seems surprising, considering that we're talking about a star, an entire sun of its own, approaching within 10,000 to 20,000 astronomical units, AU, of our solar system. That's roughly 1/5 to 1/3 of a light-year, and in cosmic terms, that's close. But gravity operates according to well-understood rules, and distance matters. What we find, reassuringly, is that even a star like Gliese 710, despite its mass and momentum, will not significantly tug on the inner architecture of our planetary system. Let's break this down with a deeper dive into gravitational influence and scale. The Sun dominates the solar system's gravitational field out to an incredible distance. The planets, including Jupiter, our largest, are locked into stable orbits governed almost entirely by the Sun's mass. Even Jupiter, the most massive planet in the solar system, exerts only a tiny fraction of the gravitational pull that the Sun does on Earth. So when we ask whether a star like Gliese 710 could disturb the Sun itself or alter the orbits of the inner planets, we need to compare not just mass, but distance and the strength of the gravitational field at those distances. The gravitational force exerted by one body on another diminishes with the square of the distance between them. At 10,000 Australian dollars, Gliese 710 would be over 250 times farther from us than Pluto, and vastly farther from the core planetary region of the solar system. For perspective, Earth's orbit is just $1 Australian from the Sun, and even Neptune, the farthest recognized planet, is only about $30 Australian away. Gliese 710's closest approach would be more than 300 times farther out than Neptune. At that distance, even though Gliese 710 is a star, its gravitational pull on the inner planets is millions to billions of times weaker than that of the Sun. In fact, its gravitational influence on Earth would be negligible, comparable to that of a large asteroid several million kilometers away. It's not that Gliese 710 is too small or weak, it's that gravity spreads thinly across space, and by the time its pull reaches the inner solar system, it's little more than a whisper. But what about the Sun? Could a massive stellar flyby tug on our own star, perhaps shifting its position minutely or pulling it off its galactic path? Yes, but the scale of that shift would be imperceptible by any meaningful measure, especially given the Sun's own motion through the galaxy. The Sun is already hurtling through space at approximately 828,000 kilometers per hour, 514,000 miles per hour, as it orbits the Milky Way. Gliese 710, though significant in mass, is like a ship passing near another ship in a vast ocean. They may subtly alter one another's wake, but not their fundamental course. Any deviation in the Sun's path caused by Gliese 710 would be incredibly minor, amounting to a tiny deflection angle, and one that has no impact on the gravitational balance of the planetary system orbiting it. One way to understand the difference between inner solar system and outer solar system perturbations is through the concept of the Hill sphere, the region around a celestial body where it dominates the attraction of satellites. For the Sun, the Hill sphere extends out to about 100,000 Australian dollars. Within that sphere, the Sun is the primary gravitational influence, and Gliese 710's closest approach would fall well within it. However, just being inside the Hill sphere doesn't mean an object exerts a meaningful gravitational disruption. Gliese 710 would need to approach within just a few hundred AU or less to pose any real risk of disturbing planetary orbits, and even that would primarily affect outer planets or objects in the Kyper belt. Another way to test for significant disruption is by simulating orbital trajectories. Astronomers have run countless n-body simulations, factoring in the mass, velocity, and projected path of Gliese 710 against the known orbits of the solar system's planets. The result? No significant changes. The planets remain locked in their courses. Their perihelions and aphelions, their inclinations and eccentricities, none are expected to shift in ways we'd even detect. Earth, Mars, Jupiter, and all the rest will continue on their million-year journeys around the Sun, unaware of the distant visitor gliding through the void. What Gliese 710 can disturb, as discussed earlier, are the objects at the edge of the solar system, the icy bodies in the Oort Cloud, and possibly some extreme trans-Neptunian objects. These are held so loosely by the Sun's gravity that even a subtle nudge from an external source, especially a massive one, can shift them from near stasis into high-speed plunges toward the inner solar system. These objects, however, are vastly different from the stable, tightly bound planets closer in. It's also worth noting that the geometry of Gliese 710's approach matters greatly. It's not heading directly toward the center of the solar system but rather is expected to pass on the outskirts, from a relatively shallow angle. This means that the vector of its gravitational pull on the inner system is not strongly aligned with the planetary orbital plane, the ecliptic, further reducing its ability to distort or disturb the compact planetary orbits. To summarize in more grounded terms, Gliese 710's gravitational fingerprint on the solar system will be real, but subtle and distant. Like a breeze brushing the leaves of trees at the edge of a vast forest, while the towering trunks in the center remain unmoved. So while the media and public may latch on to the drama of a star heading toward the solar system, the truth is less apocalyptic and more nuanced. Gliese 710 is not coming to shatter worlds. It is not going to unbind the planets from their orbits, fling Earth into the interstellar dark, or ignite gravitational chaos in the solar interior. The Sun will continue its nuclear fusion undisturbed. The planets will maintain their ancient choreography. Day will follow night, season after season, long after the star has come and gone. But the ripples it may set off far beyond Pluto, those we must watch. And perhaps that's the real story, not that Gliese 710 threatens what is close, but that it reminds us how vast, fragile, and interconnected our cosmic home truly is. It is a visitor that will brush the edges of our realm, quietly, silently, and in doing so, may set into motion stories that won't unfold until long after humanity has left its first footprints on other worlds. The idea that Gliese 710 might not be traveling alone evokes a deeply fascinating question. What if this orange dwarf star had a hidden companion? Perhaps a massive exoplanet, or even a brown dwarf, moving alongside it through the interstellar void, unseen in current observations but still bound by a shared gravitational dance. It's an idea born of speculation, but not without scientific precedent. After all, the universe has proven again and again that stars rarely journey alone. In fact, more than half of all stars in the Milky Way are in binary or multiple star systems. Some travel with stellar twins, others with distant dim partners, and still others with smaller substellar companions, planets, brown dwarfs, or massive rogue objects that blur the lines between star and planet. Given this prevalence, it's not at all unreasonable to ask, is Gliese 710 hiding something? Let's explore the possibilities. If Gliese 710 were accompanied by a brown dwarf, this would be a companion of immense interest. Brown dwarfs are often described as failed stars, too massive to be planets, but not quite massive enough to sustain hydrogen fusion like proper stars. They occupy the mass range between about 13 and 80 Jupiter masses and are generally cold, dark, and difficult to detect. Many brown dwarfs emit faint infrared signatures, which can be picked up by powerful observatories like WISE, Wide Field Infrared Survey Explorer, or JWST. However, if a brown dwarf is closely bound to Gliese 710 and relatively dim, it could remain hidden from detection at great distances. What would it mean if Gliese 710 had such a companion? The gravitational consequences would be immense, especially if this brown dwarf passed alongside the primary star into the solar system's Oort cloud. Rather than one object disturbing the outer solar system, two massive bodies would arrive, each contributing their own gravitational influence. This could significantly increase the number and diversity of objects perturbed. In other words, the scale of potential disruption would rise dramatically. This would also complicate the orbital models we've relied upon to chart Gliese 710's trajectory. Most calculations assume a single star moving through space under known velocities and directions. But if a secondary body, particularly a compact and massive one, is co-orbiting Gliese 710, it could cause oscillations or wobbles in the star's path, subtly altering its future position. Even a small orbital dance could translate into thousands of AU of variation over 1 million years. That uncertainty would ripple down into our predictions of how many comets are disturbed, how quickly they're sent inward, and what regions of the solar system may be most affected. Even more compelling is the idea of massive rogue planets, or gas giants tagging along with Gliese 710. These objects, ranging from a few Earth masses to multiple times Jupiter's mass, could be in wide, cold orbits, making them almost impossible to detect from Earth's current vantage point. If such a world were trailing just a few hundred AU behind Gliese 710, it would likely be invisible in visible light, and nearly indistinguishable from background noise in infrared surveys. Yet the possibility is not so far-fetched. In 2016, scientists discovered Scholz's star, a low-mass binary system that passed within 0.8 light-years of the Sun about 70,000 years ago. At the time, it likely caused some small perturbations in the Oort cloud. Scholz's star is itself a binary system, composed of a red dwarf and a brown dwarf. Its discovery, after the fact, reinforced the idea that low luminosity, fast-moving objects can go unnoticed until they are already upon us. So, what would the implications be if Gliese 710 had a hidden companion? First, the region of gravitational influence would be expanded. Instead of a solitary point of mass cutting through the Oort cloud, you'd have a multi-body gravitational system producing overlapping tidal forces. Comets that might have remained untouched under the influence of a single star could be destabilized by the complex gravitational interplay of two. Second, there would be a potential risk of temporary captures. If the brown dwarf or planet passed sufficiently close to some Oort cloud objects, it could trap them into temporary orbits, pulling them out of the Sun's domain, only to fling them back later on different, possibly Earth-crossing paths. This kind of celestial slingshot effect could greatly increase the unpredictability of comet trajectories, even tens of thousands of years after the flyby. Third, if the companion is massive enough and enters closer to the solar system than Gliese 710 itself, its trajectory might deviate substantially due to the Sun's gravity. In an extreme case, the companion could be slowed down, or even temporarily captured into a solar orbit, becoming a quasi-satellite of the Sun for a brief epoch. While such an outcome would be extraordinarily rare, it could open an entirely new field of study, observing how stars or brown dwarfs interact with solar systems dynamically, in real time. Now let's venture even deeper into the speculative. What if the companion isn't just a natural object? What if it were something artificial? Could a highly advanced civilization, using a brown dwarf or massive exoplanet as an ark or mobile habitat, be traveling with Gliese 710? While this borders on science fiction, some have theorized that low-temperature, long-lived stars or substellar objects could serve as energy-efficient mobile platforms for hypothetical civilizations, particularly those seeking to survive the death of their own stars or to explore the galaxy at sublight speeds. If this were the case, Gliese 710's flyby could be more than just a gravitational event. It could be a rare interstellar encounter with another intelligent lineage. But even if we remain grounded in the natural sciences, the idea of an unseen companion remains a matter of empirical interest. Future observations by Gaia, JWST, and the Roman Space Telescope may reveal subtle movements or unexpected gravitational anomalies in Gliese 710's path, clues that it is not alone. Even if the companion is never directly imaged, it may leave its mark in how Gliese 710 behaves as it approaches the solar system. Ultimately, if Gliese 710 does arrive with a companion, be it brown dwarf, rogue planet, or icy moon, it would not only amplify the potential chaos in the Oort Cloud, but also serve as a rare laboratory for studying multiple-body stellar flybys, something rarely observed in the galaxy. It would also underscore a cosmic truth: space is never empty, and stars are rarely solitary. In the end, we may look up at the orange glimmer of Gliese 710 in the far future and wonder, what else is hidden in that faint light? What shadows move beside it unseen? If history is any guide, the universe often holds more than it first reveals. And sometimes, the most important visitors are the ones that don't shine at all. Long before Gliese 710 even begins to stir the icy tendrils of the Oort Cloud, astronomers on Earth are already laying the groundwork for what may become one of the most significant observational campaigns in human history. While the flyby itself is over 1 million years away, the implications, particularly a potential rise in long-period comets, demand vigilance, planning, and innovation starting now. And that's exactly what is happening. We are preparing. Quietly. Methodically. Brilliantly. Let's start with the fundamentals. Even though the perturbation of the Oort Cloud won't peak for another 1 million years, the comets that get nudged from their cold storage today could still take thousands, or even tens of thousands, of years to arrive in the inner solar system. So, in theory, Gliese 710's gravitational effects could begin to subtly manifest within tens of thousands of years before its closest approach. This means the clock is already ticking. At the forefront of our preparation is an ongoing global effort to catalog near-Earth objects, NEOs, long-period comets, and trans-Neptunian objects. These efforts are being conducted by a network of international observatories, universities, space agencies, and private space firms, coordinated loosely under umbrella programs such as NASA's Planetary Defense Coordination Office, PDCO, ESA's Space Situational Awareness, SSA, program, and the International Astronomical Union's Minor Planet Center. But the jewel in the crown of our future efforts is the Vera C. Rubin Observatory, formerly known as the LSST, Legacy Survey of Space and Time, slated to become operational in the near future. Situated atop Cerro Pachón in Chile, this observatory is designed with one core mission: to image the entire southern sky every few nights with extreme sensitivity. Its wide-field camera, one of the largest ever built, will detect faint, fast-moving, and distant objects with unprecedented accuracy. It's not just about finding asteroids anymore. The Rubin Observatory is expected to increase the number of known long-period comets by more than tenfold. These are exactly the kinds of objects that would be ejected from the Oort Cloud by a passing star like Gliese 710. And even more critically, Rubin will provide the first long-term dataset to allow astronomers to track statistical changes in comet influx rates over time. If Gliese 710 does trigger a distant wave of icy missiles, Rubin will be the first to sense the ripple. Meanwhile, Gaia, the European Space Agency's ultra-precise astrometric mission, continues to refine the trajectory of Gliese 710 itself. Gaia has already provided the stellar position and motion data that confirmed Gliese 710's close future encounter. But as it gathers more data, it will narrow down the uncertainties surrounding the star's mass, speed, and approach angle. If there's a previously unseen companion object tagging along, or if the trajectory has any wobbles from gravitational interactions, Gaia will likely be the mission to reveal them. In tandem, researchers are running high-resolution simulations of Oort Cloud interactions, using powerful supercomputers and n-body integrators to model the chain reactions initiated by stellar flybys. These simulations are becoming more sophisticated, factoring in millions of particles, three-body effects, and chaotic orbital perturbations. Already, some of these models have shown that even modest gravitational nudges from distant stars can result in comet showers lasting tens of thousands of years, spaced irregularly, with distinct bursts of activity. So while we cannot prevent Gliese 710 from passing close to the solar system, we can use it as a predictive tool. By comparing modeled scenarios of comet influx with actual observed comet rates over the next centuries and millennia, we can reverse engineer and verify Oort cloud structure, formation models, and long-term solar system dynamics. But perhaps the most futuristic and ambitious responses are those centered on planetary defense. Yes, we're already thinking about it. Earth has survived countless minor and major impacts throughout its geological history, but now, for the first time, we have the tools to prevent one. And the first practical demonstration of that was DART, NASA's Double Asteroid Redirection Test, conducted in 2022. DART deliberately collided a spacecraft with Dimorphos, a small moonlet of the asteroid Didymos, altering its orbital period. It was humanity's first attempt at changing the trajectory of a celestial object. The mission was a success. And more importantly, it opened the door to a future in which Earth might one day deflect a dangerous comet, perhaps one born of the Oort Cloud, launched toward us by Gliese 710's distant gravitational touch. Of course, redirecting a long-period comet is significantly more challenging than pushing an asteroid. Comets move faster, are often more loosely bound and volatile, and may only be detected with months or even weeks of lead time. But DART was just a beginning. The next steps include developing intercept vehicles, kinetic impactors, laser-based ablation systems, and potentially even nuclear deflection methods, though those remain controversial. In the meantime, early warning is key. And that's where missions like Surveyor, a proposed NASA space telescope designed specifically to hunt for near-Earth objects in infrared, will play a vital role. Infrared surveys are particularly useful for detecting cold, dark comets that are invisible in visible light. If launched, Surveyor will greatly increase the chances of spotting incoming long-period comets well before they approach the Sun. Meanwhile, private initiatives are also emerging. Companies like Astroscale, Lea Labs, and Planetary Resources are exploring space debris removal and asteroid mining, but in the process, they're developing tracking systems that could also be repurposed for planetary defense. Public education and international cooperation are part of the preparation as well. Today, there are annual planetary defense conferences, where researchers simulate asteroid impact scenarios and test international responses. Though these exercises currently focus on near-Earth asteroids, the underlying infrastructure, the communication protocols, emergency planning, and international coordination could be adapted in the far future to address a surge in comets, should one ever arise. And finally, there is the philosophical preparation, the cultivation of a long-term perspective. Preparing for an event that will not happen for another 1.29 million years requires a different kind of thinking. It requires multi-generational continuity, institutional memory, and interdisciplinary resilience. How do we ensure that knowledge of Gliese 710's approach is not lost over epochs of human cultural evolution? How do we ensure the data, the models, and the alerts survive the test of time? One answer lies in intergenerational knowledge preservation, such as encoding astronomical records on ultra-durable media, like sapphire disks, DNA-encoded archives, or digital etchings on metal plates stored in deep archives. Some scientists even propose leaving astronomical warning messages on the Moon or other planetary bodies, outlasting terrestrial catastrophe. It may seem extreme, but it's not fiction. The sky remembers. The stars return. And we must too. Gliese 710 may not be a threat today, but we know it is coming. And for the first time in the history of this planet, we are not unprepared. We are charting the star. We are modeling its impact. We are watching the deep space from which its consequences may emerge. In this, we turn a future danger into a present opportunity, to build a legacy of preparedness that spans not decades or centuries, but geological epochs. An act of cosmic responsibility. In the deep recesses of time, long after our monuments have eroded and our languages have faded into forgotten echoes, the sky will host a silent visitor, a star, faint and unassuming, crossing the dark gulf between constellations. It will arrive not with fury or flame, but with a gentler kind of menace, the whispered chaos of gravity, reaching out from light years away, stirring the most ancient corners of the solar system. Gliese 710, a quiet orange dwarf, a mere ember in the tapestry of the Milky Way, will make its pass. It will shine no brighter than a candle in the void, yet behind that dim shimmer will lie the potential to alter the course of countless icy bodies, worldlets that have slumbered untouched for billions of years, buried in the Oort Cloud's glacial exile. And as this traveler moves silently through our periphery, its gravity will comb the edges of our system like a rake through ash, dislodging comets that will begin journeys as long as epochs, their destinies aimed toward the warming pull of our sun. Some will fall inward. Some will break apart. A few may wander endlessly between the stars. And perhaps, among those few, one will find itself colliding with a rocky planet, our world, sparking firestorms, reshaping oceans, rewriting evolution. Or perhaps all will miss, their arcs grand but benign, celestial messengers flashing through the sky with tails of fire, a spectacle seen by our descendants, if any remain, as portents or omens or simply breathtaking lights. We will not be there. Not as we are now. The world we know, its cities, machines, boundaries, names, will likely be dust. But perhaps, just perhaps, our knowledge will endure. That a long-vanished species once charted the path of a far-off star, mapped its course across the eons, and warned of its coming. That we, primitive in tools but rich in thought, glimpsed the mechanics of eternity and etched them into record. In this sense, Gliese 710 is not just a star on a path. It is a mirror to our significance and our fragility. It reminds us that while we may feel central, we are part of a larger dance, a choreography dictated not by human will, but by the motions of suns and ice and space. This visitor from the void carries no weapon, no malice. Its approach is slow, inevitable, and impartial. And yet, within that impartiality lies power, the ability to reshape the outer solar system, to trigger rains of comets, to whisper across the billion-year silence of the cosmos and remind us that stillness is never truly still, and nothing, no matter how remote, is untouched by time. Gliese 710 does not roar. It does not blaze. It moves with patience, wrapped in silence, wrapped in ice. But its legacy, when it arrives, will not be silence. It will be motion. It will be memory. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.